everyone. In this video, we will discuss about natural language processing. So this is one of the module in artificial intelligence. This is very important module that you have to understand in detail because we all know that AI is being ruling the world, and most of the times we will be handling the unstructured text. So like we are going to have a deeper understanding on how this natural language processing work. So let us try to understand what this natural language processing means, right? So sometimes what happen, like whenever we receive the emails from someone, and it is, you can see that emails might be placed in the spam folder. Have you noticed that? Like if you get into the spam folder and look into that, you can see a lot of similarities in the subject lines, right? And also sometimes what may happen is like you might have missed a phone call, and immediately you can see that like you can get a transcript on a voicemail in the mail inbox or the smartphone app, right? Or else like whenever you try for something, or you're trying to get some or sometimes you are googling it to get some content, and sometimes the topic will be suggested, right? Or the entities could be suggested, or the category tags, right? So what are these basically, right? So whatever I'm talking over here, like you could see something related to the text. That's what I'm saying. Yes. So you are seeing Bayesian spam filtering, which is a statistical NLP technique that compares words in spam to valid emails to identify junk mail. So what do I mean over here, right? So whenever we talk about mail, it could be a spam mail or it could be a ham mail, right? We do not know. See, like when how the system or the machine is understanding whether the mail is a spam mail or a ham mail, whether it is the more important mail or it is not really an important mail. It could be a mail that is a marketing mail. So how it is finding out that, right? So this is a crucial question sometimes that we get in our mind, right? And also we can see something like speech to text conversion, right? So that is also an NLP capability. And sometimes when we use NLP methods to search or topic modeling, entity extraction, or content categorization. So what does that basically mean? Just imagine that I am a HR and I'm giving an advertisement on LinkedIn or some of the platforms for the jobs, right? So what is happening is I'm receiving around 1,000 resumes, and like how I'm going to handle all the 1,000 resumes. It is impossible to look into all the 1,000 resumes, and I cannot take any decision on that, right? So what can I do now? What I can do now, like I may be using a model called entity, named entity recognition model. So from that, I can get to know about the location, the skill, or the organization where the person has worked before, or else like it could be like whatever information I can extract, that can be extracted, right? So these are all basically the natural language processing model. So what is meant by natural language processing? It is a branch of artificial intelligence that helps computers to understand, interpret, and manipulate human language. So what does this do? This fills the gap between human communication and computer understanding, right? So like in case when you try to enter into a website, sometimes in some websites you might have noticed this, it will be asking you, hi, how are you, and what do you need from here, right? So have you all seen that? So basically it is behaving like a human, and it is trying to fill the gap between human communication and computer understanding. So a processing of natural language is required when you want an intelligent system like robot to perform as per your instructions when you want to hear a decision from a dialogue-based clinical expert system, right? So you can say that the input and output of an NLP system can be speech or written text, right? Fine. So, like, if we have to understand about this NLP, first of all, we should know what is structured data and what is unstructured data. So let us try to understand over here. You can see number of rows and columns over here, right? So this is something looking like an Excel. Yes, so it can be displayed in rows, columns, and it could be some relational databases, right? Right. So that's clear, right? Fine. So that's about that. And the second one, you can see that it could be based on numbers, dates, and it could be something like string. It could be like CSVs, Excel files, right? And like it is estimated 20% of the enterprise data is basically the structured data, and it requires only less storage, and it is easier to manage and protect with the legacy solutions. But what are these unstructured data? So let me tell you, say for example, I have a company or I'm selling some products. So when people purchase the products from me, they will be writing in a forum about the feedback of the product that they purchased from me. So it could be positive feedback or negative feedback. And when we talk about structured data, it is going to be inside the rows and columns. So there is some structure over here, but you can see here there is no rows or columns. People write in a way whatever they think. It could be images, it could be audios, it could be videos, or it could be emails or spreadsheets, right? So most of the times 80% of the data are unstructured data, and the storage wise also it requires more storage, and also it is difficult to manage and protect with the legacy solutions, right? So these are the major differences between structured and unstructured data. So now in terms of AML part, if you look into that, it can be structured data can be easily used by machine learning algorithms, right? And also it can be easily used by business users, and it can be increased access to more tools, right? So it is easily used by machine learning algorithms. It is usually used by business users. It can be increased access to more tools. So what I mean over here is the structured data has the benefit of having in use for longer, or historically it was the only option. What I mean is there are more tools that have been tried and tested in using and analyzing structured data. So the data managers have more product choices when they use this structured data. So what are the cons of the structured data? Like I can say that it is a predefined purpose limits you. Say for example, when we write schema data definition, it's a large benefit to structured data. It is also true that the data with the predefined structure can be used only for the intended purpose. So this limits its flexibility and use cases. And when we talk about the storage options, the structured data is generally stored in data warehouses. So the data warehouses are data storage systems with the rigid schemas, right? So if there are any change in the requirements, means updating all that structured data to meet the new needs, so that it will result in expenditure of resources and time. So sometimes the cost can be mitigated by using a cloud-based data warehouse. So as this allows for greater scalability and eliminates the maintenance expenses, right? So if we talk about the examples of structured data, it is actually an old familiar friend, because it is basically the basis for inventory control systems and ATMs, and it can be human or machine generated, right? So let us understand unstructured data. So as I told you, it is in its native format and it cannot proceed until it is used, right? So which is known as schema on read. So if you look at the freedom of this unstructured data, it has the freedom of the native format. The data is not defined until it is needed. So this leads to a larger pool of use cases, because the purpose of the data data is adaptable, so that it allows the data scientists to prepare and analyze only the data needed. So the native format also allows for a wider variety of file formats in the database. So the second one is that it is faster accumulation rates. What do I mean over here is another benefit of unstructured data is like data accumulation rates. So there is no need to predefine the data, which means it can be collected quickly and easily. And the third one is about data lake storage. It is often stored in cloud data lakes, which allow for massive storage. So it allows for pay-as-you-use storage pricing, which helps cut cost and allows for easy scalability. But what are the drawbacks of using unstructured data? It requires data science expertise, right? Because it cannot be handled by everyone. A standard business user cannot use this unstructured data because it is undefined or it is not formatted nature, right? So it requires understanding the topic or area of the data, but also of understanding how the data can be related to make it useful. And the second one is about the specialized tools. Right, so not only to the expertise, it also requires some specialized tools to manipulate. So like what is happening here is standard data tools are intended for use with structured data, so which leaves a data manager with a limited choices in products for unstructured data. So some of which are still in their infancy. So it is basically like if we try to understand the examples of this unstructured data, it is qualitative rather than quantitative, which means that it is more characteristic and categorical in nature, right? So this is what the differences between structured and unstructured data. And there is another one which is about semi-structured data. It refers to what would normally be considered unstructured data. That also has metadata that identifies certain characteristics. So it contains some information to enable the data to more efficiently cataloged, searched, and analyzed than strictly unstructured data. So an example of semi-structured data versus structured data would be a tab, a delimited file containing customer data versus a database containing CRM tables, right? So on the other side of the coin, semi-structured data also has more hierarchy than unstructured data. The tab delimited file is more specific than a list of comments for from a customer's Instagram, right? So hope this is clear about the understanding the differences between structured data and unstructured data, right? So this is really important. Like when we study about this NLP, like we will be handling with the unstructured data most of the cases, right? So let us try to understand what is this natural language properties. So as I told you, NLP is a branch of AI that helps computers to understand, interpret, and manipulate human languages like English or Hindi to analyze and derive its meaning. So, and also it helps developers to organize and structure knowledge to perform tasks like translation, summarization, named entity recognition, all those kind of stuffs, right? So like let us try to understand how this basically what are the properties of the natural language, in the sense like it could be related to grammar, which is basically rule based, and the second one is about the vocabulary and hybrid language. The fourth one is connotation. So what do what do I mean by connotation, because this word can be new to you. So what I try to mean over here is connotation means, say for example, I'm using a word called handicapped. Okay, so I'm using a word called handicapped. So now if you look into the word, this looks like something negative. So sometimes people use the word called handiable, though it carries equal meaning. Sometimes no, both may bring like some kind of no, like when you call it as handleable, it could be something positive, right? And there could be ambiguity in the sense, say for example, I'm saying like bear, right? So BAR. When I say that, it could be noun at the same time, it could be sometimes verb also, right? So basically this differ, right? The next one is about the slang. What do I mean by slang? Slang in the sense I'm talking about the internet slang. Say for example, nowadays we are writing lot of messages in the WhatsApp or in the internet, and or say for example, let me write something like instead of love, we sometimes write it as LUV. So we may understand what this basically mean. Can we expect the laptop or the computer or the machine to understand what this that this love is basically? This love means this. Or else sometimes we are using some hashtags, or else sometimes like we are using short forms like TTYL, right? And sometimes hello we write this way and all, right? So how the computer or the machine will understand these differences among all these, right? See, there are it's really interesting, right? Because the natural language in the sense like however even when we talk about grammar, we call it as rule based, like there are certain rules, right? uh, and sometimes we use symbols or strings that no are right. So there are lots of things we should really understand about this properties of natural language. And there are two kind of stuff we should understand. One is about natural language understanding, and what is this natural language understanding, right? Like mapping the given input in natural language into useful representations, or it could be like analyzing different aspects of the language. The second one is like natural language generation. So here, what's happening over here, the text is being planned. So it includes retrieving the relevant content from knowledge base, or it could be like sentence planning. It includes choosing the required words, forming meaningful phrases, and it is setting tone of the sentence. And the next one is like text realization, and it is mapping sentence plan into sentence structure, right? So let me also tell you, actually, we are going to do a lot in this NLP. Let me give you some interesting examples of NLP, like text classification, machine translation, named entity recognition, speech recognition, spell check, automated query in answering, sentiment analysis. See, we must have come across all these terms in our life, but we may not know what is that, right? So we do not know even that is actually related to this NLP, right? Sometimes when we write messages in the WhatsApp, it is showing you the recommendations, right? So we have seen all these, but now in this module, we will try to understand what it means. What does this actually tells us? So what are the advantages of NLP? So users can ask questions about any subjects, and so that they can get the response within the seconds, multiple response within seconds. And also NLP system provides answers to the questions in natural language. The NLP system offers exact answers to the questions, and no unnecessary or unwanted information, right? And also the accuracy of the answers increases with the amount of relevant information provided in the question. And NLP process helps computers to communicate with the humans in their language and scales other language related tasks. And also it allows us to perform more language based data when we compare to a human being without fatigue, and in an unbiased and consistent way, right? So sometimes when we talk to humans, like when we ask number of questions, there is a high chance that there is a high possibility of biasness over there, but that we cannot expect with this NLP. So what are the disadvantages of the NLP? Like complex query language, the system may not be able to provide the correct answer. The question that is poorly worded or ambiguous. So if there are any ambiguities, the system may not be able to understand, right? And this is being built for a single and a specific task only. So it is unable to adapt to new domains and problems because of its limited functions, right? And also NLP system does not have a user interface which lacks features that allow users to further interact with the system, right? So these are basically like we tried to understand in this lecture, like what is NLP, what are the advantages, what are the disadvantages, and what is the difference between structured and unstructured data, and what are the challenges while dealing with the unstructured data.
In this video, let us discuss about pre-processing in NLP. So what is NLP? NLP is nothing but natural language processing. So why it is really required to understand natural language processing, right? So we are trying to teach the computer to learn languages, and then also we expect that to understand it with suitable, efficient algorithms, right? So we may be familiar with the Google's keyboard, which suggests autocorrect or word predict and more, right? So there is another tool called as Grammarly, which is a tool for content writers and professionals, and it makes sure their articles look professional. So how does it work? It uses YAML algorithms to suggest the right amounts of vocabulary, or it could be tonality, and it could be much more than that, right? So that the content is written professionally apt and it captures the total attention of the reader. And the next one is about the translation systems that use language modeling to work efficiently with multiple languages. So why do we give more importance to this NLP nowadays, right? So we all know that people are nowadays involved with the languages and they are trying to understand the patterns in languages, which are called as linguists, right? So Wikipedia is the greatest source for that, right? So the field of computational linguistics began with an interest. It tried to understand the patterns in data, or it could be parts of speech tagging, easier processing of data, various applications in the banking and finance industries. It could be educational institutions, and there are many more, right? So how does this work? So what it does, how does this NLP basically work? So it converts the unstructured data into computer readable language, right? So it converts the unstructured data into computer readable language by following attributes of natural language. So machines employ some complex algorithms to break down any text content to extract meaning from it. So that is really required, right? So we have to get the meaning of it, right? So the collected data is then used to further teach the machines the logics of natural language. So the natural language processing uses two kind of analysis. Say one is about syntax, and the second one is about semantics, right? So the natural language processing uses several algorithms to follow some grammatical rules, right? So it uses some grammatical rules which are then used to derive meaning out of any kind of text content. So like we can see like a lemmatization, morphological segmentation, word segmentation, part of speech tagging, parsing, stemming, sentence breaking. So we will be trying to understand each and everything, right? So this is basically the syntax. The second one is about semantics. So this is comparatively difficult process where machines try to understand the meaning of each section. So semantic means it is about the meaning. It tries to understand the meaning of any content. It could be both separately and in context. So even though semantical analysis has come a long way from a binary disposition, there is still a lot of room for improvement, right? So the major thing is about NER. NER means named entity recognition. It is one of the primary steps involved in the process, which segregates text content into predefined groups. So word sense disambiguation is the next step in the process. So it depends upon the contextual meaning, right? So this is what we are going to understand, like why natural language processing is important. We all know that the data is being generated every day, and as we discussed, 80% of the data is most of the time the unstructured data. So NLP enables computers to read this data and convey the same in languages humans understand. Say it could be, we may have some medical record, unstructured data. Let us see some example for that. It could be medical records. So sometimes like a government data, like census data, something like that. So most of the times these kind of data are unstructured, right? So say, for example, you're writing some feedback about the product that you purchased from a particular website, right? So once that is being done, the computers analyze these text and speech to extract the meaning of it, right? So people sometimes ask me why the advancement is required in the field of NLP. So please try to understand that NLP is the process of enhancing the capabilities of computers to understand the human language. So when we talk about the databases, always it is of the structured form of data, right? But unstructured data, most of the times the data we take from internet or almost unstructured data. So in such case, understanding human language and we have to know, we have certain goals. Say, for example, Alibaba voice assistant, we must have heard about it, right? So there we try to master non-linear conversations. Non-linear conversations means which is something related to humans' manner of communication. So say, for example, we are talking about one thing in first sentence and suddenly we try to talk about the next, then we come back to the first topic, right? So the person listening to this understand the jump, but how the computers will understand, right? So this is why we really give more importance to this field. So nowadays, if you look into this NLP professionals are in lot of demand. So I can tell you for sure that once you once you master in NLP, you will be getting a lot of opportunities over here. And because as I told you, unstructured data has lots of information and that can help companies to grow and succeed. Say, for example, when you monitor tweet patterns, that can be used to understand the problems that is existing in the societies, and it also can be used in the time of crisis. So understanding and practicing NLP is surely a path to get into the field of machine learning, right? So in case if you look into the applications of a few more applications of NLP, I can say Grammarly, if you see, it could be used in MS Word or Google Docs or anything, right? So search engines, or it could be used in voice assistants, news feeds, translation systems. So there are many more, right? So when you desire to study NLP, you should have programming knowledge in Python, Keras, right, and then NumPy. What I try to say over here is you should also learn the basic of how to clean text data, manual tokenization or NLTK tokenization, right? So there are several models that we will be coming across soon, right? And also we have to be familiar with some open source like NLTK and then Stanford toolkit, right? Stanford toolkit, and then GenSim, and then Open NLP, right? Okay, fine. Hope this is clear, right? So let's try to understand pre-processing in NLP over here. First of all, let me tell you that what is text wrangling means. We call it as pre-processing or wrangling, whatever it is. Like we are, getting we are doing a machine readable form and we are formatting text from raw data, right? And whenever we collect text from various sources, it may have a lot of noise because these are unstructured data, right? So when we pass the data text from the various data sources, we need to make sense of the unstructured property of the raw data. So the text cleansing is used in the majority of the cleaning to be performed, right? So we know machine learning needs data in the numeric form. So we basically use encoding techniques like bag of word, bigram, n-gram, TF-ID of word to vector, so that we see to encode text into numeric vector. But before encoding, we should first clean the text data. And this process to prepare or clean text data before encoding is basically called as text pre-processing, right? So whenever we start with a task, it is always important to clean the data first. So to clean the data, in the sense we are making the data to be understandable by a machine, right? So what are the steps, they are really required to do that, right? So there may be the next question, like what factors decide the quality and quantity of cleansing? So I can say that one thing is about the parsing performance. It could be about the source of data source or the external noise, right? So what is meant by this text cleansing, right? So here, we are trying to clean the text and to remove the noise surrounding the text, and that we call it as text cleansing. Data munging or data wrangling, like people use different terms over here, but anyways, like people use it interchangeably in a similar context, right? And so first, when we start with pre-processing, let us try to understand what is sentence splitter. So always, like NLP applications require splitting a large files of text data into sentences. So what will happen is always the text data could be of large files, right? So what we want is, like, we want to convert it into meaningful data, right? We have to convert it into meaningful data. So how it can be done? It can be the large files of raw text can be broken into small sentences, right? So a sentence is the smallest unit of conversation. So how do we define like something like a sentence for a computer, right? So we say that sentence as the small unit, right? Sentence as the small unit. So how do we define this? So we need it because it simplifies the processing involved. So for example, the period can be used as a splitting tool where each period signifies one sentence. So say, for example, I have to extract dialogues from a paragraph, and like we are searching all the sentences, we could see some special characters, or we can see some inverted commas or the double inverted commas and all, right? So a typical sentence splitter can be something as simple as splitting the string on, right? So to something as complex as a predictive classifier to identify the sentence boundaries. So what is this tokenization? Tokenization is nothing but it is defined as a minimal unit, right? It is a minimal unit that a machine understands and processes at a time. So here all the texts and strings are processed only after they have undergone tokenization, which is basically the process of splitting the strings into meaningful tokens. Hope it is clear, right? So the task of tokenization looks complex because such as like need of the NLP application or the complexity of the language itself. Say, for example, if you consider English, it can be as simple as choosing only words and numbers, right? But in case if you take some Dravidian languages, on the other hand, it could be hard because of the vagueness present in the morphological boundaries between words, right? So let us understand what is this tokenization. Like, it is the process of splitting a given text into smaller pieces called tokens, right? So words, numbers, punctuation marks, and others can be considered as tokens. So we use natural language toolkit library for tokenization, and here each word is a token. So when we talk about tokenization, the paragraph can be converted into sentences, the sentence can be converted into words, right? Say I ate an apple. So how do we tokenize this? I ate an apple. So if there are any alphanumeric characters over there, how do we handle it? And if there are any special characters like apostrophes or inverted commas, how do we handle it? Like in case if there are two-word entities like New Delhi, how do we handle that, right? So these will be the questions that we try to understand in NLP, right? Fine. The next thing is about the stop words. So what are stop words? Stop words are the most commonly occurring words. Say, for example, I'm asking like, how are you? So R could be stop word here, right? So it does not add any weightage or meaning to the sentence. So just it is working as a bridge, and its job is to ensure that whether the sentence is grammatically correct or not, right? So it is the most commonly used pre-processing step in NLP application. So I think like removing the words that occur commonly in the corpus is the definition of stop word removal, right? So majority of the articles or pronouns are called as stop words, right? In case like if you perform a task of information retrieval or classification, these cannot be affected by stop word. So stop word removal is not required in all the cases. But on the contrary, NLP application stop word removal has a major impact, right? So like the stop word list for a language is a hand curated list of words that occur commonly. So stop word lists are mostly available online. Like a simple way is to make use of the words document frequency, right? So word presence across the corpus is used as an indicator for classification of stop words, right? So how does this stop word removal help? What are some of the alternatives for stop word removal? That and all we have to think about it, right? So the stop words are the most common words in a language, like the me is to all, right? Do you think it has any meaning? No, actually it is working as a bridge or to fill the gap between the words in a sentence, right? So we can remove the stop words using a natural language toolkit, as I said, articles like and common verbs like is, was, were, are, pronouns he, she, it, conjunctions for and, prepositions on and with. So these are basically some examples of stop words, right? So now let us try to understand what is normalization. Say we have to, we may want the same token for different forms of the word. Like say, if you take book or books, both of them are giving the same meaning to us, right? So in case if you consider both tokens in the single one, say book, books into book, talk, talks into talk. So that could be really helpful, right? So that's basically called as normalization. Right, so the next one is about stemming. So what is this stemming? Stemming means it is a process of obtaining the root form of the word, right? So here there are certain rules Using that, all tokens can be cut down to maintain or to obtain the root word. It is a rule-based process. So here we club together variations of the taken. So let's say that, like, okay, so I take an example like study, right? It could be studying or study. So anyways, it is going to give the same meaning as I told in the last slide, right? So it does not make sense to differentiate between the two, right? So we use stemming to club both grammatical variances to the root word. So it is in use for its simplicity, right? But in case of Dravidian languages with many alphabets and thus many more permutations of words possible. So the possibility of the stemmer is identifying in the rules is very low. So in such cases, we use lemmatization instead because it is a robust, efficient, and methodical way of combining grammatical variation. So we will look into the differences of both. You can see here, like when you do this stemming, what is happening? People is changed to PEO, PL, saying is changed to say, says is changed to say, and the components is converted into component, and paid is changed to pay, says is again say. So if you look into the says, saying has converted into say, and troubling is changed into TROUBL. So if you look into this, you can understand that there are okay, say, pay, those are meanings. But again, if you look into this compound or trouble, TROUBL, there may not be a proper meaning to it, right? So when we talk about stemmer, there are several types of stemmer, one is like porter stemmer, Potostemmer. There is another one called as Loven stemmer, right? There is another one called as Drawson stemmer, and there is another one called as Crowet stemmer. See, what I'm saying is maybe very little. There are many more actually, right? So Potostemmer, generally we use Potostemmer a lot, and it makes use of a large number of rules and no, with a lesser morphological variation. So for complex languages, custom stemmers need to be designed, right? So on the contrary, what I'm trying to say here is there are a lot of stemmers like snowball stemmers. We use snowball stemmers for other languages like French, German, Italian, English, Portuguese, right? So stemming is the pre-processing step. So nowadays, in the modern NLP applications, this is being excluded because it basically depends upon the domain and application of interest. When NLP taggers like a part of speech tagger, dependency parser, or NE are used, right? So let us understand, what is lemmatization now. So here finding the lemma of a word is the more exact task. So you can look at the same example now. Says is changed to say, took changed to take, paid is changed to pay, saying, say, troubling is changed to trouble, right? So this is really important to understand. So what it does is it converts the grammatical or inflected forms of the root of the word so it use the context and POS tag to find the inflected form of the word, and various normalization rules are applied for each POS tag to get the root word, right? So it is really interesting. So what is the difference between stemming and lemmatization? What would the rules be for rule-based stemmer for native language? Would it be simpler or difficult to do so, right? So we have to look into this in detail. So the basic difference between stemming and lemmatization is that stemming is converted into the root word, but again, there is no meaning for it. But in lemmatization, there is a proper meaning, right? So there are some other cases like rare word removal. So what do I mean by rare word removal? Because there could be some words which are very unique, like it could be the name of a product or brand, or like some could be like noise characters, and that can be removed, right? So say for example, like when we handle a task of text classification, there are several names which is not a feasible option to use. So we know that, say for example, Adolf Hitler, his name is an exception. So usually names do not signify the emotion, or it is not really required to do that, right? So the second one is like spell correction. So spelling should be checked for in the given corpus, because the model should not be trained with the wrong spellings, because the outputs generated will be wrong. So spelling correction is not a necessity, but can be skipped if the spellings don't matter for the application, right? So what is dependency parsing? So it is basically to identify the dependency parts of a sentence to understand the relationship between the head words. So it helps to establish a syntactic structure for any sentence to understand it better, right? So these type of structures can be used for analyzing the semantic and syntactic structure of a sentence, right? So it is not only can the passing tree check the grammar of the sentence, but also its semantic format. I told you already, right? Semantic means it is about the meaning, right? So the pass tree is the most used syntactic tree and can be generated through parsing algorithms like early algorithm, right? So any given sentence having more than one dependency parse assigning the syntactic structure, and it can become quite complex. So multiple parse trees are known as ambiguities, so which has to be resolved in order to for a sentence to gain a clean syntactic structure. So actually what we have seen is the basic pre-processing techniques, what we generally use, like tokenization, stop word, and what kind of normalization do we do, like stemming, lemmatization, right? So I hope this is clear to you. In this video, let us discuss about the bag of words and TF and IDF, right? So we all know that making machines to understand text is being a challenge. So how the challenges can be overcome, right? See, for example, the human beings are able to understand what the other people are talking to us within a fraction of a second. But can you imagine machines to understand that? What they have to do? So they need us to break down the text into a numerical form so that the machines will be able to understand the text in the form of numerical. So this is where the concepts of bag of words and TF and IDF come into play. So let us try to understand how these BOW, which means bag of words, and TF IDF, right? So those techniques help us to convert text sentences into numeric vectors, right? Okay, so let us try to understand that. Okay, so just imagine that people are going to watch some movie. So once they watch the movie, they will be writing some comments about the movie. So can we say that all the comments or all the feedbacks will be of the same level, or all the feedbacks will be the same? It is not, right? So one person may say that the movie was really good. The other person may say that the movie was not as expected. The person three may say that it is a normal movie, nothing much different from the other movie. So something like that, right? So we may get any kind of reviews from the people. So now we can see contrasting reviews about the movie. And like here, when you look at 10,000 or 1 lakh reviews about these, we can get a lot of interesting insights about each, about the movie from different perspectives, right? So we cannot simply give these sentences to the machine learning, because we know very well that the machine learning models will not be able to handle it. It cannot basically analyze whether the statements or whether the reviews are positive or negative. So what are we trying to do? We have to do some pre-processing techniques, right? So that is what we have to do, right? So like a pre-processing, not only pre-processing, like we call it as sentiment analysis, like that has to be done, right? So here we are going to discuss about a bag of words as well as TF IDF. Okay. So first let us understand how to create vectors from text, right? So that's what I said. There will be text, right? So there are texts. So basically there are some reviews. So reviews in the sense like that is in the form of text, and that has to be converted into the form of vectors, right? So this is what we are trying to do. Fine, right. So the technique that we use over here is called as word embedding, where we can represent the text using vectors, right? So we are going to look into two popular word embedding techniques. One is BOW, which means bag of words, and the second one is TF-IDF, which means term frequency, inverse document frequency, right? So by the end of the video, you will be clear with both the concepts, right? So let us try to understand what are bag of words model. So when you look at the model, this is actually the simplest form of text representation in numbers. So as the name suggests, it is a bag of words. So it is a bag of word vector. Word vector means nothing but a string of numbers. So let me tell you that it is a technique that is used in text modeling, and it is a method of feature extraction with the text data. And this is very simple and flexible way of extracting features from documents. Now look at this. There are three statements over here. This movie is very scary and long. This movie is not scary and slow. This movie is spooky and good. So now when you look at these three statements, it is saying that very scary, here not scary, here spooky. This looks like very scary and long in the sense sometimes we can think that as a negative statement, and here not scary and slow is also looking like some kind of negative statement. This looks like a positive statement. So how are we going to make the machines to understand whether the review is positive or negative, right? So what will happen is first a vocabulary will be created for the unique words. So what will be the vocabulary consist of? So that could be this movie is very scary. So let me underline all those vocabulary now. 1, 2, 3, 4, 5, 6, 7, right? And 9. And scary is already there, and is there, is there, maybe the slow, and then this is there, movie is there, is there, spooky, right? So what is happening here? The first step is that vocabulary is generated. A vocabulary is created, right? Now the next step is that we can now take each of these words and mark their occurrence. How many times it has occurred? Say, for example, if I take this, this, you can see that here there is one this, here there is one this, here there is one this, right? So this is how we are going to see that like the occurrence, the number of occurrences being identified, right? So review 1, review 2, review 3. So this one movie is very scary and long. In the first statement, there is no not, no slow, no spooky, no good. If you take the second statement, it is given that this movie is not. So not in the sense where it's not here uh, actually like scary, right? And the second time it is saying that scary is already there, right? And is slow, right? So you can see that slow over there, right? So where is the slow over here? and here you can see 1 over here, right? So this, the third one is this movie is spooky and good, right? So where is that and good? So now you can see that like now the vector is being written as 1 1 1 1 1 1 1 0 0 0 0 0. So the length of the review in words is 7. So the second case, 8 words. So let us see over here 1, 2, 4, 5, 6, 7, right? So what is the error over here? Let us try to find out that. I think this movie is not scary, right? Actually, that is there. So there should be one over here. So this movie is not scary, right? Is not scary, right? And is so 2 is there and 2 is slow, right? So 1, 2, 4, 5, 6, 7, 8, right? Right? So this is basically 0. So we are getting it as 8. Hope this is clear, right? Okay, fine. So the third step is that this movie is spooky and right, spooky and that should be like a good, right? And that should be like a good, right? So now what you can see over here, 1, 2, 3, 4, 5, 6, 7, right? So how many are there? Basically, here there are 7 words, right? Because the statement is this movie is spooky and good, right? So there should be this movie is uh, uh, okay. So spooky and good. So basically, this is also right. So let me make the change over here. So this is 6, right? So hope this is clear now. Now you can write it in the vector form, right? So this is being the number, whatever is being written over here, that will be written in the form of vectors over here, right? So hope this is understandable, right? So let me clear this now. So like you can look into this, the quick brown fox jumped over the lazy dog's back. Now is the time for all good men to come to the aid of their party. So if you look into this word aid, in document 1, it is not there, but in document 2, it is there for once. And all in the sense, like if you look into this here, there is 1 and 0 back, right? So if you look into this back, actually 1, document 2, it is not there, right? So this is how it is being there, right? So document 1 and document 2, it is written over here. So if you look into this, these are all stop word over here, right? So we know what are stop words, right? Which does not bring any meanings, right? So if you look into this, you can say that maybe here for is not meaningful, and like is not meaningful, of where is of. Okay, so whatever are the stop words, so that list can be taken, right? So this is about bag of words. Now let us try to understand what are the drawbacks of using this bag of words model. So here we can see that we will be facing issues when we come across the new sentences, because it can work only for the available sentences. So if the new sentences contain new words, then our vocabulary size would increase, and the length of the vectors also will increase, right? So additionally, the vectors will contain many zeros, and so that it will result in sparse matrix, actually, which is that we would like to avoid. So the vectors would also contain many zeros, in the sense like we could see zeros over here, right? So basically we want to get rid of it, right? And also we are retaining no information on the grammar of the sentences, nor on the ordering of the words in the text. We are not bothering about that also, right? So this is about the bag of words model. Now let us try to understand what is term frequency. So TF-IDF is another statistic that's intended to reflect how important a word is to a document in the collection or corpus. So what does that basically mean? TF is equal to, that is term frequency is equal to number of or occurrences of word in particular document divided by total number of words in document. Okay, so let us understand that in the numerator, n is the number of times the term T the number of times the term appears in the document, and thus each document and term would have its own rule. So how can I understand this? So in case if you take the same example over there, right? So same vocabulary we can use like that what we used in bag of words model. So let us try to understand. So vocabulary is this: movie is very scary and long, not slow, spooky and good, right? So the number of words in review 2 was equal to 8. So a term frequency for the word this. So let us try to understand that number of times this appears in review 2 divided by number of terms in review 2. So that is how it is being taken. Say for example, when this movie is taken, out of 8, how many plays this movie has occurred, right? So I have taken the second sentence. So you can see that in the second sentence, movie is okay. So let me write the sentence so that it would be helpful to understand it little more. So I can say that, okay, so let this be the sentence now. Now what you can see over here, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, and slow, right? 1, 2, 3, 4, 5, 6. Okay, twice I have typed that. Right. So you can see that there are 8 words over here. Movie has appeared only once. If you take is, it has appeared twice. That's why I have written 2 by 8, which is equal to 1 by 4. So very is not there. That's why we are writing it as 0. And scary is there only one time out of 8 and has appeared only once. So this is how it is being written. So hope this is clear. So this is how term frequency is being found. So we can, let us write for all the 3 sentences now. So review 1, review 2, review 3. So for all the cases it is being written, right? Okay, clear now? So now let us try to understand what is this inverse document frequency. It is a measure of how important a term is. So how we find is like we will be finding the logarithm of number of documents divided by number of documents that contains that particular word basically, right? Say for example, here we can say that how many statements are there? 3. So in case if you are trying to find out no this, okay, let us take this as the example. So how many documents are there? 3 documents. So how many in how many times it has appeared in that 3 times? So what I can write now, log of 3 by 3, which is equal to log of 1. So what I'm trying to say over here is how many documents are there. So here actually we were talking about 3 statements, right? So we were talking about 3 statements over here. So basically that will become 3 divided by how many times that word appears in all documents. So if you look into that, this has appeared in all the 3 documents. So log 3 by 3, that will be equal to log 1. So what will be the answer now? This will be equal to 0. So similarly, you can find out for all the other words too, right? So you can find out for all the words 0. Movie has also appeared in everything. So 0 is 0. Very 0.48. Scary 0.18. So what do you understand from this? So here you can see that is this and so these are all having IDF as 0, which means that it has less importance. But if you look into that, scary is 0.18, long is 0.48, and if you look into that, good is 0.48, right? There are few words which are really important to understand how the movie is like. So these all have low values, and it means that it has more importance, right? So now what are we trying to find out? We are trying to get TF into IDF. So what does this basically mean? Term frequency into inverse document frequency, right? So this is what we are trying to understand. So what is this term frequency? Term frequency means the number of times divided by the number of terms in the document, right? Number of times it has appeared divided by number of terms. And IDF is nothing but number of documents divided by number of documents with that particular word, right? So this is what we have seen. So now let us try to understand this. This is being written over here, review 1, review 2, review 3, and we have IDF. We are finding out TF IDF, TF IDF, TF IDF for all the cases, right? So now we have got the TF IDF scores for the vocabulary, and TF IDF also gives a larger values for less frequent. So if you look into this is less, movie is less, is less, but you can see that very more here it is less. So now you can compare all these scores. Basically, it will tell you that TF IDF gives larger values for less frequent words, and it is high when both TF and IDF are really high. So whenever TF and IDF are really high, it is giving us a higher value, right? When both TF and IDF are high, we are getting it as the higher value. So what can we conclude from this? TF IDF gives large values for less frequent words, and it is high when both values are high, right? So the word is rare in all the documents combined, but frequent in a single document. So what we have seen here, bag of words just creates a set of vectors. Bag of words just creates a set of vectors containing the count of word occurrences in the document, while TF-IDF model contains information on the more important words and less important ones as well. And bag of word vectors are easy to interpret, but TF-IDF usually performs better in machine learning models. So hope this is clear to you, right? So this is the understanding about bag of model and TF-IDF. Hope this is clear to you. In this video, let us discuss about NLP data pre-processing, right? So let us try to understand this. So in the first step, what I have done is I have imported NLTK. NLTK is nothing but natural language toolkit. From NLTK, I'm downloading this PUNKT, right? So I'm downloading this package basically in case if you get the output as true, then our work is being done. So the next step, what I'm doing is from NLTK.tokenize, import sent underscore tokenize, comma word underscore tokenize, right? So let me tell you that what is happening over here, right? So sent underscore tokenize means what it will do is when I give some paragraph, that will be converted into sentence, that will be tokenized into sentences, and like the sentences can be tokenized into words. So look here, so I have a text over here. Text is equal to natural language processing is a field in artificial intelligence and is related to linguistics. On a high level, the goal of NLP is to program computers to automatically understand human languages and also to automatically write or speak in human languages. We say natural language to mean human language and to indicate that we are not talking about computer languages. Let us study the pre-processing steps in NLP. We need to know about the libraries for NLP. So let me run this code and I'll show you like what is happening now. Just I want to see the type of text. So it is saying that it belongs to the type string, right? So in case if I want to get the length of this text, so what is the text over here? This text, right? So I want to get the length. So what I'm getting is 485, right? So what I'm doing now, send is equal to send underscore tokenize of this text basically. So I'm rewriting this sent again and print of sent underscore tokenize of text. So what is happening over here? Just you can look at the code now. Natural language processing NLP is a field in artificial intelligence and is also related to linguistics, right? So this is basically one sentence. The second sentence, what you can see, on a high level, the goal of NLP is to program computers to automatically understand human languages and also to automatically write or speak in human languages. So this is basically the second sentence. The third sentence I'm getting, we say natural language to mean human language and to indicate that we are not talking about computer programming languages. Let us study the pre-processing steps, right? So this is what happening over here. So now what I'm doing, I'm going to tokenize these into words. So what I'm writing, words is equal to word underscore tokenized text. So when I get the output, what I'm getting, natural is separate, language is separate, processing is separate. So basically I'm getting tokens that are nothing but the words, right? So what I have done is say from NLTK dot probability input freq dist. So basically I'm trying to get the frequency distribution of words and what are the most common. So from this, what I could figure out is 2 has appeared 7 times and this comma has appeared 4 times. NLP has appeared 3 times, if has appeared 3 times, in has appeared 3 times, right? So now I'm importing matplotlib.pyplot as PLT and just I want to see the plot of this. So what I can see over here is for 2, I'm having 7 and basically for this comma, I'm having 4 and NLP I'm getting 3, yes, also I'm getting 3, in also I'm getting 3, right? So now what I'm doing, no punk. Okay, so basically I'm creating an empty list now. I'm creating an empty list now. So for W in words, so I'm creating a for loop now. So if W is alpha, no punk dot append W dot lower, print no punk, and here this is to create a new line and I want to also get the length of this no punk, right? So what I could see over here is like a natural language processing. So what is happening? If you look over here, you could see a lot of pronunciation over here, but now those are not there, right? So what is the output now? Output I'm getting it as 73 now, right? So then now free f dist equal to freq dist no punk f dist dot most underscore common. So what I'm getting now, so here I had a comma. Now I'm not getting that comma. So what is happening? 2 is 7 and then NLP is 3, yes is 3, in is 3, the same thing I'm getting, and also language is 3. So what has happened over here? This comma is being replaced since I have removed those punctuations. What I'm getting is just, other than that, what is the next one which has more frequency? So the model is identifying the language, right? So from NLTK dot corpus import stopwords. Stopwords equal to stopwords dot words English, print stopwords. So what I'm doing here, I'm trying to import these stopwords, right? So basically I'm giving that from English, I want to see the stopwords. So what are these stopwords? These stopwords are used as a bridge in languages basically. In case if you take English, so these stopwords may not carry any meaning over here, but at the same time, like if it is not there, it may not nice to look at those sentences. That is the reason it is being used as a bridge in all these sentences. So what I'm doing, I'm getting for English, right? So from NLTK dot corpus import stopwords. So I'm getting stopwords from English, right? So once it is being done, I have to remove the stopwords now. So again, what I'm doing, I am creating stopwords and empty list. And for W in no punk, basically no punk in the sense like we have removed the punctuation. If W not in stopwords, stop underscore words append W, and I'm printing all the stopwords, right? So what is happening over here? I am getting all those really required, right? So I am getting natural language processing, NLP field, artificial intelligence. So I'm getting output as 42. So just look at over here, it started with a 485 And finally, now we are getting it as once we do this, no punctuation, it is being converted into this. And this is what we are getting 42, right? So what I'm doing now, again, I'm creating FDIST, frequency dist for stop words, and the most common over here. So what I'm getting, language 3, NLP 3, human 3, natural 2, also 2, right? So this is what being happen now. Now what I'm doing is like I want to do stemming, right? So let us try to understand what is this stemming. Stemming is, like, say for example, I have words like believe, believing, believed, believe. So that may not be really required to have all the words. Otherwise, the number of count or the characters are going to be higher. To minimize that, what I'm doing is I'm using this Porter stemmer. So from nltk.stem import Porter stemmer. So Porter is equal to Porter stemmer, and then I'm giving the list over here. For W in list, print Porter.stem. So this is the output I'm getting, BELIEV, right? So this is the output I'm getting. So when I do with this WordNet lematizer, Lima is equal to WordNet lematizer, and these are the list. This is the list basically behaving, believe, studies, believe. And for W in list, I'm printing lima.lematize of this, basically this W, right? So behaving, believe, studies, believe. So what is the difference we can see over here is when you give believe, believing, believed, believes in Porter stemmers, when in stemming, you are getting the output as the same. That's for this case particularly. And like if you consider this word, there is no meaning for this word, right? Basically, BELIEV. In case if it is E, then fine, okay, there is a meaning. But there is no meaning over here. So now you can understand here over behaving, believe, studies, believe. So what are we getting as the output? Behaving, believe, study, believe. So basically what is happening here is everything is converted into the root word, which is having the meaning. So similarly, the next one, what I have tried is from nltk.stem import WordNet lematizer. And here I have given the list as where, was, are, am, right? So it is trying to identify this basically, and I'm getting output as BBBB. So what does this mean basically? So what is happening here? So this where, was, are, am. So everything is almost the same word, which is equivalent to BE. That is why we are getting as the output, right? So in case if you want to do POS for the same, what you will get for believing, studies, teacher. So if you get that, believing, you are getting it as VBG, verb and gerund. And here studies, you can get about noun singular, and teacher also we are getting as plural, right? So this is how basically this technique work. So in this video, we had a discussion regarding how to tokenize into sentences or the words. And also we tried to understand, we tried to convert it into lower, right? So when I used this lower, what happened previously, it was in capital N, now it is changed into a natural C. Because why we are doing this? Because in some sentences, artificial may be the first word, in some cases it could be in the middle. At that time, it should not consider both as a different term, right? So that's the reason it is being done. And then we remove punctuation, and then we have seen how to use this stemming and lemmatization. Hope it is very clear. Sentiment analysis. So have you ever heard this word sentiment analysis anywhere? Okay, say for example, you are purchasing a phone or a laptop from specific website or from a store, okay? So whenever you purchase a product, if you are really happy with the product, you may go and write it in the website or in the specified forum about that particular phone or the product, whatever you purchase, right? Even in case if you do not like it also, you may write about the feedback in that provided forum. Now, you are a customer over here. So just think from the business person point of view. He should know whether he is able to please the customers, whether he is able to make the customers happy, or the customers are not really happy with the product, or else the business people also want to know whether they have to improve on any point of view, right? So this is where the sentiment analysis pitch in. Whenever you write some feedback or the comments or the reviews on the forum, the business people will try to understand whether it is a positive statement or a negative statement or a neutral statement. Right. So what is sentiment analysis? Sentiment analysis is a supervised machine learning technique that is used to analyze and predict the polarity of sentiments within a text, either positive or negative. So we may be wondering what is this polarity? So polarity for now, just you can think that whether it is about positive or negative, right? So it is used by the companies and the business people to understand their user experience, emotions, responses, so that they can improve the quality and flexibility of the products on the services, right? So how this can be done? So first of all, we need data about the feedback, right? So we all know that data is the heart of every machine learning problem. So in terms of machine learning, no problem can be solved without without the data. So we are trying to collect the data from the forum, right? So let's try to understand the pipeline in sentiment analysis. Whenever we handle any task in machine learning, we follow certain pipeline, right? So here the first pipeline is that pre-processing text and building vocabulary. So here we will be trying to remove these stop words, punctuations, URLs, and any special hashtags, which is not really giving any meaning or values to that particular model, right? And then adding unique pre-processed words to your vocabulary, right? And then the second step is about feature extraction. So this will be iterating through each and every data example to to extract the features using a frequency dictionary and finally create a feature matrix. The third step is the training model. So now we will be using the feature matrix to train a logistic regression model or any model in order to use that model for predicting sentiments. Then it is about the testing model. So using our trained model to get the predictions from data it has never seen, right? So the first step, what I said, was about pre-processing data. So we all know that this is the most important and crucial step in the pipeline, because this is the most important thing that's going to add value to the model, right? So pre-processing takes first step is, say, tokenization. Tokenization means what? Say, like the person will be writing the feedback in a sentence. It is basically an unstructured data. So the sentence has to be broken into words, right? So that conversion is basically called as tokenization. Tokens means words over here, right? And then we will be trying to remove the URLs. We'll be trying to remove the stop words, say then punctuation, stemming, lower casing and all, right? So let me tell you, say there is a statement, right? The movie was awesome. And the person is very much excited and he has used this exclamation mark also. So what will happen in the first step? What do we say? Tokenization. So what will happen? It will get converted into tokens. So the movie was awesome are the tokens now, right? So the next step that URLs and handles, no URLs over here. Stop words can be removed. So what are the stop words? The can be removed, was can be removed, and then when it does punctuations, this can be removed. So we will be having only these two. Excuse me. We will be having only two words over here. One is movie and the next one is about awesome, right? Right, we have only these two, movie and awesome. Then stemming means like, okay, here the stemming is not really required. Lower casing means like, okay, anyways, it is being removed already, right? So this is how the pre-processing the data is being done, right? right? So this is how the pre-processing is being done. Then the next step is that after pre-processing the data, we have to create a vocabulary. It could be bag of words, or it could be bag of words, or basically just to create vocabulary that will store each word and assign some numeric value to each distinct word in the sense like the tokens, right? So we all know that machine learning algorithms cannot work on the raw text directly. So we have to use some feature extraction techniques to convert text into a matrix or vector of numerical features, right? So it's a naive approach to extract features of a text. So according to this parse representation, we can create a feature matrix by iterating through the entire data. And for each word in the text example, we will assign 1 at the position of the word in the vocabulary list. And for non-occurring words, we will assign 0. Okay. So for so our feature matrix will be having rows, which is equal to total sentences in our data, and columns equal to total words in the vocabulary. So actually what are we doing? After pre-processing the data, we create a vocabulary that will store each unique word and assign some numeric value to each distinct word, right? So this is what happening. So while working with the language processing, there could be another problem is handling the raw text directly. So that is the reason we are going ahead with this feature extraction techniques, right? And then like we have seen about sparse representation, and here the disadvantages of this is actually it may require large training time, and the prediction time could also be larger, right? Like in the feature extraction, the positive frequency means what? The number of times a word occurred in sentences with a positive sentiment, and the negative frequency is being done the number of times a word occurred in sentences with a negative sentiment, right? So a frequency dictionary keeps track of the positive and negative frequencies of each word in the data, right? Say, for example, the sentence, I'm happy. So it will be trying to identify in how many places it is being positive and how many places it is being negative, right? So here, using frequency dictionary for feature extraction, we can reduce the dimensions of the each row by representing each sentence on a feature matrix, right? So features of a text data are extracted with a feature dictionary using this following formulae, right? So you can see that xm, which is equal to 1 summation frequency, right? W comma 1 frequency W comma 0. So this is basically the features of tweet m, and this could be the bias. This could be some positive, some POS frequencies, which means some of positive frequencies, and this could be some of negative frequencies, right? So this is what will happen. Now what will happen for the words in the vocabulary? The positive frequency, negative frequencies will be noted. So we will be having the three-dimensional feature vector for a single tweet, right? So we will be having dimensional feature vector for our tweet, right? So now we have to iterate through each and every example to extract features of each example. Then we will be using those features to create the feature matrix, right? So now here you can see that this is how the model is being trained, right? You can see that initialize the parameters, and we will be initializing our parameter theta that we can use in our sigmoid. So here I have, in case if we are using logistic regression, we initialize our parameter theta that we can use in our sigmoid. We then compute the gradient, right, that we will use to update this theta, and then calculate the cost, right? So we will keep repeating the steps until the cost minimizes or converges, right? So this is how the model is being trained, right? So how to test the model now? Okay, so how we will be doing the testing the model now? We have to split the data into X validation and Y validation sentiment, then use feature extraction for this X underscore validation to transform text into numerical features, and find the vector H is equal to sigmoid for each text in the validation set. then map some function to get the actual classes while comparing with the threshold, then we can find the accuracy of the prediction. So accordingly, we can find out the sentiment, right? So this is how we can do the testing of a model, right? So now let us see how we can use it, how we can do it using algorithm. You can see over here, I have written like from text blob, import text blob, right? And then I have written the first sentence, test one is equal to text blob. I have written the movie was awesome, right? So when I try to test this sentiment, it is returning me polarity 1, subjectivity 1. So polarity is 1 means it is a positive statement, and also subjectivity is also saying that it is 1, right? And then I'm trying with the movie was terrible. This is very easy. Even someone, when a person here also, he can understand that it is a negative sentiment, right? The same thing, the machine is also identifying that polarity is -1 and subjectivity is 1, right? Say, for example, I'm writing like this, the movie is not that good. Okay, the movie is not that good. So in this case, the polarity is being taken as 0.875 and subjectivity is taken as 0.6, right? Then the fourth statement, what I have tried is, I think he went to temple. So here, the statement could not predict anything related to the sentiment, right? That is why we are getting it as 0. And the next one, the food served at the park was great. The park was great. Okay. So let me run all these sentences once again. So when I say that the food served at the park was great, now I'm getting polarity as 0.8 and subjectivity as 0.75. So let me make it to not great. Now you can see that the polarity is changed to -0.4, which means it is a negative sentiment. Hope I'm very clear with this positive and negative sentiment, right? So first of all, you have to understand why sentiment analysis is really important in business point of view, because all the businesses are dependent on the customers. So we actually value the customers' feedbacks and the reviews. So this sentiment analysis is going to be a very important task in the field of NLP, right? Hello, everyone. In this video, we are going to understand the most important topic in natural language processing. So we are going to discuss about language models. So what is meant by language model, right? So it is a statistical tool which is used to predict words. So let me give a simple example, right? So you are talking to one of your friends and like he starts saying something. Before that, you may be predicting that what he is going to complete, right? So this is a psychological way, or whenever we talk to our friends or whenever we talk to someone, or like by listening to few words in the statement, then we really try to understand what the particular means to say, right? So a language model is a statistical tool to predict words. So for example, there are a lot of weather models, right? So it predicts the 7-day forecast. So language models try to find out the patterns in the human language. So predict the patterns in the human language means they are used to predict the spoken word in and see, like basically it tries to identify the next word or the next the next word in a particular sentence, right? So we all know that images have dominated the field of AI. Similarly, the language models are the next frontier for artificial intelligence. So images were more accessible for modeling tasks because they are easier to label and they have computer interpretable information already, which is being encoded in pixels. But this language modeling is being more challenging for modelers because language is complex. Language has layers of meaning. Language changes from context to context. Language changes from sentence to sentence, author to author. See, If I speak something like it could be related to something like which may be related to my domain, or when somebody else speak, it could be related to his domain, right? So sentences are also harder to label than so a language model learns to predict the probability of a sequence of words. Say, for example, like I have given an example, right? The is a single word. So from this the, we cannot predict anything. So the next the word gold is added to that, the gold. Okay, so what is it about, right? This is how the mind thinks. Now the third one is the gold price. So we are going to talk something related to gold price. And the next one is about the gold price fell. And the next one is about gold price fell again. So it's going to talk of something related to from the past. It is connecting to something, right? So again today for a third day. So I have not written everything because that's why I have kept dot. So fell again today for this, I mean, the gold price, no, the gold price fell again for a third day. So like it could be about the gold price, it could be about the stock, right? So when we get to know that the third day or no, it could be third minute or whatever it is. See, for example, the stocks fell again today for a third. So once it end, like it could be like a third day or what it basically, right? So this is what we are trying to identify. So similarly here, the gold price fell again. So here also we are trying to predict this, right? So what are we doing over here? We can narrow down the choice of next word and sometimes even get it right. Fine. So this is what we are trying to understand now. So basically we will try to understand how these language models basically work. We all know that computers can only read numbers, right? So computers can read only numbers. So in order for a language model to be created, all words must be converted to a sequence of numbers for the computer to read, right? So for modelers, we call these as no encodings, right? So this encodings can range in complexity. At the basic level, every word can get its own number. So this is basically called a label encoding. So label encoding assigns one number for each unique word in a sentence. Say, for example, I have an example, the boy sat by the tree, something like this, right? So we could represent the sentence by certain numbers like 1, 2, 3, 4. So again, this is the, so I'm going to write it as 1 and the next one is 5, right? So this is the most basic encoding one could give a set of words, right? So when we talk about this no language model, in 2014, word2vec was discovered, right? Word2vec was discovered, and like it was being a very popular encoding method. After that, encodings have greatly evolved from label encoding methods to one-hot encoding methods to word embeddings. And 2019, from 2019, we are using transform, right? So language modeling got a big popularity boost in 2019 with the development of this transformer. So last year, 2019, there were 4 major releases of sophisticated transformers, which was being provided by Google, OpenAI, and Salesforce, right? So these transformer models given by OpenAI and Google, they have a lot of computer resources to build, right? And another one I can say that Hugging Face, right? So this is also being used. So now you may be thinking like, what are the challenges, no? What are the potential challenges or benefits of these language models? So in modeling, if we try to predict the, say for example, grade on an exam based on how many hours we studied and whether or not we had our dinner, we would say that the model has 2 parameters. So in the first case, what I said, it was one thing related to time spent studying and whether we had dinner or not, right? So the transformer models these companies have released have been trained on 1.5 billion parameters and are often so big, right? And they can't work on most computers or mobile devices, right? So when OpenAI released its GPT-2 model, it came with several caveats, right? The company said it was a new technology and they wanted to see how the release of the language model would be used by developers first. So the language models pose a threat to disinformation, right? So it poses a threat to disinformation, where deep fakes are putting out fake videos of people. Language models can be used by bad parties to create junk news or increase catfishing scams through fake text messages, emails, and social media status updates. So articles generated by a machine continue to be released that look like other people actually wrote them, right? So, but the models may also have a place in the creative arts, which we are only just beginning to see. So Hugging Face made its models available in an interactive user interface, right, with the transformer. So anyone can see how the technology basically work, right? So it is actually funny to play with, even if it doesn't serve a functional writing purpose, right? So like in the real world where we use it means like Google has included some auto completion services in its Gmail, Gdocs, G Sheet services. So it is being used to help coders write better code with autocomplete and autocorrect functionality built in or as add-ons on their preferred IDEs. IDEs are nothing but integrated development environment, right? So we have reached a tipping point in the possibility and potential of language models. So before a new encoding method could increase the performance of its predecessor by 15 to 20%, now the industry is seeing its diminishing returns, and new models to arrive on the scene only have a tenth of a percentage point improvement on the old ones, right? So now let us have a discussion on N-gram model, right? So we will try to understand what this N-gram model is. So as I told you, N-gram is a sequence of N tokens. Tokens are nothing but words, right? Tokens are nothing but words. So we are talking about the N-gram modeling, that is text modeling, right? So like we will try to understand what it is. Say, for example, I love reading blogs about astronomy, right? Astronomy. So here a unigram or 1 gram is a one word sequence. So here the unigrams would be simply I love reading blogs about astronomy. So 2 gram or bigram is a two-word sequence of words like I love reading, reading blogs about astronomy, right? Something like that. And the 3 gram is a three-word sequence of words like I love reading, say I love reading about data science, something like that, right? So if we have a good N-gram model, we can predict what is the probability of seeing the word W given a history of previous words where the history contains N-1 word. So what I try to say here is, based upon the previous words, if I'm trying to find out the probability of the given word, this is what the N-gram model tells us, right? Fine. So let us look into this and then we will have a deep discussion on it. P of W1, W2 up to Wn, which is equal to P of W1 into P of W2 into W3 up to P of Wn-1. So how can I understand this better? P of the Prime Minister of our country, right? Which is nothing but probability of the into probability of prime into probability of minister into probability of into probability of R into probability of country, right? So here what we can see, probability of the prime minister of our country, right? This is what I'm trying to understand, or trying to solve now. So probability of the, that's going to be the first word. And now probability of prime, the given word is the, right? And probability of minister and prime is given. Probability of, no, this is how this actually flows, right? So in the next case, what I have taken, probability of W1 up to Wn equal to probability of W1 into probability of W1 given, sorry, probability of W2 given W1 into probability of W3 given W1 comma W2, right? So this is how this actually goes on. So I'm trying to find out this one, which is nothing but probability of the, that is probability of W1 into probability of W2 given W1. So what is the first word over here? The. So probability of prime given the. So probability of minister given the and prime, and probability of given prime minister, right? This is how it goes. So simple, right? So probability of Wn given Wn minus 1 is equal to count Wn minus 1 comma Wn divided by count Wn minus 1. Say for example, probability of minister given prime, which is equal to count prime comma minister divided by count of prime, right? So probability of trigram probability. So probability of Wn given Wn minus 2, Wn minus 1. Try to understand the difference between this and that. Here we are trying to predict this word given this, right? So here you can see that like probability of this given this and this, right? So count Wn minus 2, a count of Wn minus 2, comma Wn minus 1, comma Wn divided by count Wn minus 2, comma Wn minus 1, right? So probability of given minister, comma prime, which is equal to count of prime, comma minister, comma of, basically n minus 2, n minus 1, n, right? So we are trying to basically find out this one, right? So that is what over here. And these are the two words before that, right? Wn minus 2 and Wn minus 1 divided by count of prime, comma minister, right? So hope this is clear, right? Fine. So now let us understand this in detail, right? So what is meant by n-gram? N-gram is a contiguous sequence of n items from a given sample of text or speech. This is what Wikipedia says. So items refer to states in Markov chains. Items can be characters, words, or sentences, etc. So let me take the whiteboard. Let us try to understand this in detail. All right. So we are basically trying to understand n-gram modeling, right? So it is a contiguous sequence of n items, right? Sequence of n items from a single word. So if n is equal to 2, then it is bigram. If n is equal to 3, it is trigram. If n is equal to 1, it is unigram, and on. So in case of character, in characters or the states of Markov chains. So we had the Markov chains where we had the state, then from state A, we can go against that state. So actually it is Markov in the sense it is about a movement from one state to the another state, right? Say for example, there is an example. The parrot is flying in the parrot is flying on the blue sky, right? Flying on the blue sky, right? Say for example, I'm taking n is equal to 2. Say for example, I'm going to take according to this one. So what's happening is th, right? Then the next one will be he. Then the next one will be e space. Then the next one will be space and p. So this is how it will work. If I take n equal to 3, he space, e space p, right? So space p a. this is how it will be done, right? So here we are considering length as 2 or 3. So we can, here the window is moving as such, right? So once TH is done, then it is moved to the next window is selected, with the, even here the space is being included, right? And we are very sure that this is being moved by window, right? So this is what we have to understand, right? So it is not necessary that it should happen letters by letters. It can happen word by word also, right? So the parrot, and like maybe I'm trying to predict the third one, the parrot is. Then the parrot is, after that, I'm trying to predict this flying. The parrot is flying. The parrot is flying on. So it depends upon the gram what we choose. Are we going ahead with a bigram or trigram? That is what it depends. Hope this is clear to you. So we will be understanding these models in detail, because why we are having such a deeper understanding about this model, because this is really important when you go ahead with the modeling kind of stuffs, right? So hope this is clear to you.
Hello everyone. In this video, let us discuss about the word embedding, frequency-based word embedding. So first of all, we should understand what is word embedding, right? So let me give you an example now. Say for example, you want to find out the meaning of a sentence or the meaning of a message that is sent by your friend in WhatsApp, right? So you want to find out the meaning in the sense like your friend has texted you in, say, in some other language, right? Actually, that you do not know. So what do you do now? You type the same sentence in Google Translate, and then you will try to get the meaning of it, right? Say, for example, if you open Google and search for some articles on data science, and you can get hundreds of search results related to that. So what are these examples actually mean, right? So what is happening here? Text processing, right? Text processing. So as we all know, humans can deal with the text format quite intuitively, but provided we have millions of documents being generated in a single day, we cannot have humans performing all the tasks, right? So it is neither scalable nor effective. So how can we make computers to perform classification tasks, or say, how can we make it to perform classification or clustering, right? So we know that these are generally insufficient at handling and processing strings or text for any fruitful outputs, right? So a computer can match two strings and tell you whether they are same or not, right? So a computer can match two strings and tell you whether they are same or not. But how do we make computers tell you that whether it is the same or difficult? Say, for example, you want to make a computer to understand that apple is a tasty fruit, right? And also at the same time, apple is a fruit that can be eaten, but it is not a company, right? So when we talk about apple, it could be one is that it could be a fruit, or else it could be another. I mean, what I try to say is it could be a company, right? So how do you make the computer to understand whether you are looking for fruit or company, right? So the answer to all these questions lie in creating a representation for words that capture their meanings. Basically, you to capture their meanings, semantic relationships, and different types of context, etc. Right? So this is what we are going to see over here, right? So now let us try to understand what are word embeddings, right? So word embeddings are the text converted into numbers. So as I told you, machine is not able to understand the text. So it has to be converted into numbers. And there may be different numerical representation of the same text, right? So I think that is clear that why we are using this, no, why we are going ahead with this word embedding technique, right? So when we talk about machine learning algorithms or deep learning architectures, they are capable of processing strings or plain text in raw form. They require numbers as inputs to perform any sort of job. Say, for example, when you deal with the machine learning, we used to do one-hot encoding technique, right? And with a huge amount of data here, when we have it in the text format, it is imperative to extract the knowledge out of it, right? So, like for example, you purchase some product from say a company A or B, and you are writing reviews about it, and now the company has to identify whether the product has really satisfied the customers or not. So this basically we call it a sentiment analysis, right? So a word embedding format generally tries to map a word using a dictionary to a vector. So the sentence can be broken down to have a clear view, right? So let us understand word embeddings or the text converted into numbers, and there may be different numerical representations of the same text. So a vector representation of a word may be a one-hot encoded vector, where 1 stands for the position where the word exists and 0 everywhere else. So how can I understand this? Say, for example, I have this dictionary. Word embeddings are converted into numbers, right? So for this numbers, I have to write it, right? So what I can say 0, 0, 0, 0, 0, 1. In case if I want to write for converted, it is going to be 0, 0, 0, 1, 0, 0. So basically, word embedding is a way to convert a piece of text in a numerical format that our machines can read. So there are different types of word embeddings. One is frequency based and another one is prediction based embedding. So in this video, we are going to discuss about frequency based embedding, right? So when we talk about frequency based embedding, there are three types basically. One is count vector, the second one is TF-IDF vector, and the third one is a co-occurrence vector, right? So let us try to understand one by one. So when we talk about frequency modeling, first let us try to understand what the count vector means, right? So what are we trying to understand? What the count vector means. Say, for example, there is a corpus C of D documents. So that's why I have written D1, D2, D3 up to DD. And there are N unique tokens extracted out of the corpus C. So the N tokens will form our dictionary, and the size of the count vector matrix will be given by D cross N. So here each row in the matrix M contains the frequency of the tokens in document, right? So how can I understand this little more clear? So let me give you an example now. Say, for example, so I'm writing a sentence now. He is a lazy boy, right? And she is also lazy. So we are writing about someone saying that he is lazy boy and she is also lazy, right? So this could be a sentence. And the next one, what I'm going to write is Neeraj, or you can write any name. So I'm writing Neeraj is a lazy person, or like something else, right? Okay. I can use anything. You can write anything over there. Okay, let it be Neeraj. Okay, nothing's wrong. If there is any Neeraj over here, then only we should worry about it, right? Then also don't worry about it. This could be some other Neeraj, right? So Neeraj is a lazy person. right? So now the dictionary created may have a list of unique tokens. So what are the tokens here? He is a token, she is a token, lazy is a token, boy is a token, Neeraj is a token, person is a token. So here I can say that D is equal to 2. Why do I say D equal to 2? Because there are two sentences, right? So I'm saying that D is equal to 2 and N is equal to 6. Because what and all I'm going to consider? He, lazy, boy, she, Neeraj, person, right? So what do I get now? I'll be getting a count matrix of size 2 cross 6. Right, I'll be getting a 2 cross 6 matrix, right? So let us understand this. Okay, so let this be D1 and let this be D2, right? So I'm going to write it over here, D1 and D2, and here I'm writing he, and here I'm writing she, and here I'm writing lazy, boy, Neeraj, right? It could be person, right? I do not have. Okay, so let me erase this. Let me write this, right? So I'm going to write it as he. I'm writing she. I'm writing lazy, boy, Neeraj, and then I'm writing person, right? Okay, so first I'm going to consider what? D1, right? So I'm going to consider D1 now. So in D1, what I can say, he is there for one time, she is there for one time, and lazy. And here also I can see lazy. So that's going to be 2. And boy is 1. Basically, Neeraj is also 1. And person is also 1. Right? Oh, sorry. Neeraj is not there, right? Because we are talking about D1. So when you talk about D2, what it is going to be? There is no he, there is no she, there is one lazy, and then there is no boy, Neeraj, and person. This is what I'll get. So now a column can be understood as a word vector for the corresponding word in the matrix. Yeah. So here, if I write lazy, I can write it as lazy. I can write it as 2, 1. And here the rows corresponds to the documents in the corpus and the columns corresponds to the tokens in the dictionary. So let us try to understand. Rows correspond to the documents in the corpus, right? So how many, right? So I hope that is clear, right? And here the rows correspond to the document in the corpus and the columns correspond to the tokens in the dictionary, right? So the second row here, I can say that D2, in the D2, there is only once I have lazy. And there is Neeraj only once, person also only once. Now there could be a few variations over here. The way dictionary is prepared by, right? So in real world applications, we might have a corpus which contains millions of documents. And with this millions of documents, we can extract hundreds of millions of unique words. So basically the matrix that will be generated like this, will be a very sparse one and inefficient for any computation. So an alternative to using every unique word as a dictionary element would be to pick, say, top 10,000 words based on frequency and then prepare a dictionary. Do you understand what I mean over here? We may have a corpus which may contain millions of documents. And with millions of documents, we can extract hundreds of millions of unique words. So the matrix that will be prepared like above will be a very sparse one and inefficient. So what do we do as an alternative? Like we will be using every unique word as a dictionary element would be to pick, say, 10,000 words based on frequency and then prepare a dictionary, right? So here the way count is taken for each word. So we may either take the frequency, that is the number of times the word has appeared in that particular document, or the presence, which means like has the word appeared in the document to be the entry in the count matrix here. right? So that is what being represented over here, term 1, term 2, term 3, right? So this is basically a document vector. So there are 8 documents and here there are 8 terms, right? So this is about count vector. So the next one is about TF IDF vectorization. So this is another method. This is also frequency based method. But what is difference from the count vectorization is that it takes into account not just the occurrence of a word in a single document, but in the entire corpus. So is it rational? Right? So that's what we are trying to understand. Say there are some common words like is, the, right? So these appear to quite frequently in comparison to the words which are important to a document. For example, a document A, there is a word called a Lionel Messi is going to contain more occurrences of the word Messi in comparison to other documents. But common words like the, etc. are also going to be present in higher frequency in almost every document. So ideally what we want to do, what we want is to downweight the common words occurring in almost all the documents and give more importance to words that appear in subset of documents. So how does this TF-IDF works is it penalize the common words by assigning them lower weights while giving importance to words like Messi in a particular document. So let us understand. So here we will be using TF. TF means the number of times the term T appears in the document divided by number of terms in the document. So basically it denotes the contribution of the word to the document. That is, the words relevant to the document should be frequent. See, if a word has appeared in all the document, then probably that a word is not relevant to particular document. But if it has appeared in a subset of documents, then probably the word is of some relevance to the documents present in, right? Fine. So let me take an example now, right? Let me take an example now. Let me type it up. Say I'm writing like this is about puppy, right? So the second sentence what I'm writing is this is about say dog or cat or something like that, right? Anything you can take, right? Fine. So here in the document one is this is about puppy. This has you have to see that like how many times it is being appeared, right? So how many times it is being appeared. So what I'm saying, TF means number of times the term T appears in the document divided by the number of terms in the document. So totally there are 8 words, and here I can say that like this in document 1 has appeared 1 by 8, in document 2 has appeared 1 by 5, right? So it denotes the contribution of the word to the document. That is, words relevant to the document should be frequent, right? So in case if I try to find out IDF, which is equal to log of capital N by small n, capital N means number of documents and small n is the number of documents a term T has appeared in, right? So when I find out this, when I try to find out this IDF, which is nothing but a log of capital N divided by small n, right? So what is this capital N basically means? This is the number of documents, and this is basically the number of documents that term T has appeared in, right? So now in case if you find out the value for this, this is going to be log 2 by 2, which is going to be equal to 0, right? So this is how this is being done, and then TF into IDF, that will give us the TF IDF, right? I hope this is clear, right? So this is how the TF IDF basically work. And then now let us understand the co-occurrence matrix with a fixed context window. So now similar words tend to occur together and it will have similar context. Say for example, apple is a fruit, mango is a fruit. Apple and mango tend to have a similar context, right? Basically both are fruits. So before understanding like how the co-occurrence matrix is constructed, let us try to understand two concepts over here. One is about the co-occurrence. Okay, so you have to understand about co-occurrence, and the second one what you have to study is about context window, right? So you have to study about context window. So what is co-occurrence? For a given corpus, the co-occurrence of a pair of words, say W1 and W2, is number of times they have appeared together in the context window. I hope I'm clear, right? Co-occurrence. Co means together, right? Together occurred. So which means that I'm taking a pair of words, say W1 and W2, number of times they have appeared together in a context window. So what is context window? Context window is specified by a number at the direction. So what does that mean? Say for example, I say context window of 2. So what does that basically mean, right? So let us try to understand that, right? So let me take a whiteboard now. See, for example, I'm saying like a quick brown fox jumped over the lazy dog. So now you can see here, say for example, here these are two context window for the word fox. And for calculating co-occurrence, only these words will be counted. So in case if I am trying to find out for over, what will happen? If I want to find out for over, these two will be considered, right? So basically fox jump and then the and lazy, right? So now let's take an example corpus to clearly understand what this what this basically means, right? So this is what we are going to understand, right? So let me say that in the corpus what I have is he is not lazy, he is intelligent, right? And he is smart. Okay. Now let us try to understand what this co-occurrence matrix by seeing some examples over here. So you can see some boxes over here, red box and blue box over here, right? So red box is that how many number of times he and is have appeared in the context window 2, right? In the context window 2, and can be seen that the count turns out to be 4, right? So how I can tell that? Say he is not lazy. Okay, let me show the let me show you that and I'll make you to understand. So you can see that he is not lazy, he is intelligent, and is he, because basically I'm asking for is he is, right? So he is. So what we can find from here is red box tells us that the number of times he and is have appeared in the context window 2, and it can be seen that the count turns out to be 4. And here the word lazy has never appeared with intelligent. Here you can see that, right? The 0 corresponds to lazy as well as intelligent. So we are trying to see that lazy has never appeared with intelligent in the context window, and it has been assigned to 0, right? So what is this co-occurrence matrix? So what are the variations over here? Let's say there are B unique words in the corpus. So vocabulary size will be equal to B. So the columns of the co-occurrence matrix form the context words. So what are the different variations over here? A co-occurrence matrix of size B cross B. Now for even a decent corpus, B gets very large and difficult to handle. So this architecture is never preferred in practice, right? A co-occurrence matrix of size B cross N, where N is a subset of B, and it can be obtained by removing irrelevant words like stop words, etc. So this is still very large and present computational difficulties, right? So, but remember that this co-occurrence matrix is not the word vector representation that is generally used. Instead, this co-occurrence matrix is decomposed using techniques called as PCA, SVD into factors, and then combination of these factors form the word vector representation, right? For example, you are performing PCA on this matrix of size VXV, right? So you'll be getting V principal components. So you can choose K components out of these V components. So the new matrix will be of the form V cross K. So a single word can be represented in V dimensions, will be represented in K dimensions. So what PCA does at the back is it decomposes co-occurrence matrix into three matrices, right? And U, S, and V, where U and V are both orthogonal matrix, right? So you can see that both are orthogonal matrices. So here it is the dot product of U and S that gives the word vector representation, and V gives the word context representation, right? So now let us try to understand the advantages. So basically it preserves the semantic relationship between words. That is, the man and women tend to be closer than man and apple. That's very obvious. It also uses SVD at its core, which means it produces more accurate word vector representations than existing methods. And it uses factorization, which is a well-defined problem and can be efficiently solved. And it has to be computed once and can be used anytime once computed. So in this case, we can say that in the sense it is faster in comparison to others. See, what are the disadvantages of co-occurrence matrix? So it requires huge memory to store the co-occurrence matrix. But this problem can be circumvented by factorizing the matrix out of the system, like Hadoop clusters and all, right? So these are the types of frequency-based modeling. Basically, we have covered count vector, we have covered TF-IDF, we have covered co-occurrence matrix. Hope this is clear to you.
Dense encoding. What is the capital of France? It is the question. So the encoder technique will read, take the whole questions, put in the model, dense embedding model, and both encoder weights optimize to minimize vector difference. Okay, and then context encoder provide the answer. So here only capital and France, and what that means, someone is asking something. So if here context will be written just like Paris is the capital of that. So this is trained using multiple text, multiple parameters. You have to provide to the model. The model are able to understand that this way we have to write the text. Dense encoding. Dense means depth, or the, you can say, more data are lies on a particular position. If this is a XYZ plane, so we have a 3D diagram, okay, for the data, just like in gradient descent. If there is a depth gradient, that means there are more data which is common, or you can say you can group those words. Those data are related to a particular group, or you can say particular object. Just like that here, these all yellow dots, yellow circles, are grouped at a are dense at a one place. That means if you can see the text, Saturday, Friday, Sunday, Monday. So these are the day of a week. So that's why they are uh, placed at a very less distance. So you can understand by them, by this graph. Word are represented by dense vector, where a vector represents the projection of the word into a continuous vector space. Okay, continuous vector space means the continuously data are coming into the data space, and the data will be fetched to the model, continuously fetching and processing. So, which word are storing at what place and how it represent in the this projection? It is an improvement over more the traditional bag of word model encoding. In the previous classes, I had give you some bag of words. You can see here. This is the bag of words. That means we are creating a table, numerical table against this text. Okay. And then we are matching with this text. These are vocabulary, which is the data which is created, and this text is asked by the user. Okay. And then we are processing those all numerical data through the input layer, hidden layer. Okay. These are input layer, green, and then yellow and orange, and this pink is hidden layer, and this is our output layer. So we are connecting all those layers, processing through the numerical data, and then we'll map it that which word is asked again and again, and what will be the sentence, what is the behind left chair table, what is behind the table. Okay, so this way, what is comes one times. This is frequency. Okay, this is called frequency. 1, 2, 3. How many times? So this is the technique is called bag of words. So in this technique, words are represented by dense vector, where a vector represents the projection of the word into a continuous vector space. It is an improvement over more the traditional bag of word model. Okay, this is the another technique which can remove the disadvantages of bag of words model. So dense encoding are capable for more features. Encoding schemes where large sparse vectors are used to represent each word, just like that. Woman, queen, man, king. Okay. If king minus man plus woman equal to queen. Okay. So these are the techniques we can use to predict the output. Okay.
In this video, we are going to discuss about the most important concept, word to vec. So now look at this. So what do you understand from this? So you can see that here there is red, and here I have red, yellow, and green. The corresponding red column is 1, and the remaining 2 are basically zeros. So again, there is red, 1, 0, 0. Again, there is yellow. So I'm having 0, 1, 0, and then green. You can see that 0, 0, 1. So next for this yellow, it's going to be 0, 1, 0, right? So very simple. So something it is converting a text into numbers. That's what I could figure out from that. So let us try to understand what it is. Right? Fine. So word to vec is not a single algorithm, and it is an algorithm that takes corpora as an input and outputs it in the form of vectors, right? So technically speaking, word to vec is a model to form or create word embedding. So it's a modern way of representing word, and each word is represented by a vector. Vector in the sense what? Array of numbers based upon embedding size. So the vectors are nothing but the weights of neurons. So if we set neurons of size 100, then we will be having 100 weights, and those weights are our word embeddings or simply dense vector. So this is not a single algorithm, but here we can talk about two techniques, the most important techniques. CBOW, skip gram model. CBOW means what? Continuous bag of words. And the next one is skip gram model. So both these are shallow neural networks which map words to the target variable, which is also a word. So both of these techniques learn weights which act as word vector representations. So basically it tries to find out a relation. It could be semantic relation, or it could be syntactic relation between the words, which was not possible by our traditional TF IDF or frequency based approach. So when we train this model, each one hot encoded word gets a point in a dimensional space where it learns and groups the word with a similar meaning. So here the neural network is incorporated here is a shallow. So one thing to note here is that we need large textual data to pass into word to vec model to find out the relation within words or generate meaningful result. So what are we trying to do over here is word to vector is basically trying to find out the relationship, semantic relationship or syntactic relationship. So let us try to understand this, right? So still I can tell about this, right? You can see this over here, right? So here, what is the context word and target word? Context word. So I like natural language processing. Now here, what is happening? The natural language processing. I like natural language processing. I like natural language processing. What this basically tells us, right? So what this basically tells us, that's what we are trying to identify. Just look at this, and whatever is coming to your mind, you can just tell me. Right. So if you look into this, you could figure out. Can you figure out something from this? Yes. Right. So this is what the word to vec tells us. Next, let us try to understand CBOW, which means continuous bag of words. So the way continuous bag of words work is that it tries to predict the probability of a word in a given context, right? So this the way CBOW, that is continuous bag of words, work is that it tries to predict the probability of a word given a context, right? So a context may be a single word or could be a group of words. But for simplicity, I'll take a single context word and try to predict a single target word. So suppose we have a corpus C, which is equal to hey, hey, this is a sample corpus using only one context word, right? Fine. So the same thing I have written over here. You can see that the input is over here and the matrix here will be containing. So here it is showing us the n one hot encoded code. So this is basically the output, right? So the matrix shown in the in this image is actually sent to 3 layers. So one could be the input layer, the second one could be hidden layer, third one is output layer. The output layer is a softmax layer which is used to sum the probabilities obtained in the output layer to 1. So now let us try to understand what has happened over here. So the corpus is converted into a training set for CBOW model. So the input is given below. The matrix on the right in the below image, I mean this image, is basically giving me the one heart encoded, right? So below image in the sense like from data point 1, data point 2, what we can understand over here, hey, this is sample, right? So this sample is corpus, right? So this is how we will be getting it. Yes. So what's happening here now? The target for single data point, say for example, here I have this one, right? So in case if I write for this one, what I'm getting 0, and for sample alone, this is what we are getting for each and every case, right? So the matrix shown in this above image can be sent into a shallow neural network with 3 layers, right? So input layer, hidden layer, and the output layer, right? And here the output layer is a softmax layer, and which is used to find out the probabilities obtained in the output layer, right? So now the here what we can try is the flow is as follows. So the input layer and the target, so both are one hot encoded of size 1 into b, where v is equal to 10, right? So here we are talking about this case basically. So there will be two sets of weights. One is between the input and the hidden layer. The second one could be between hidden and the output layer. So input hidden layer matrix size is v into n. Hidden output layer matrix size is n into v. So what is n here? Number of dimensions we choose to represent our word in, and it is arbitrary, right? So here what is the n over here? N is actually 4, right? So there is no activation function between the layers. So now the input is being multiplied by the input hidden weights and called as hidden activation. So basically it is just the corresponding row, the hidden matrix, input hidden matrix copied, right? So now what will happen? The hidden input gets multiplied by hidden output weight and the output is being calculated. Now the error between output and target is being calculated and propagated back. So we know about back propagation, right? So the weight between the hidden layer and the output layer is taken as the word vector representation of the word, right? So this is what happened here. So this is basically for a single context word. Now, if we have multiple context words, how does it work, right? So that is what the question that comes to our mind, right? So here you can see the 3 context words and it predicts the probability of a target word. So the input can be assumed as taking 3 one-hot encoded vectors in the input layer, like it could be red, blue, or green. So the 3 input layer will have 3 1 cross v vectors in the input and 1 cross v in the output layer. So the remaining everything will be same as for one context CBOW, right? So the steps will be the same. The calculation of hidden activation will change. So just instead of copying the corresponding rows of the input hidden weight matrix to the hidden layer, instead of that, an average is being taken and the corresponding, the average is taken over all the corresponding rows of the matrix, right? So the average vector is being calculated and it becomes the activation, hidden activation. So say for example, if we have a 3 context words for a single target word, we will have 3 initial hidden activations. So which will be averaged element wise to obtain the final activation. So basically in both a single context word and multiple context word, we can see the images like how that basically changes, right? So here it is single, it is for multiple, right? So basically we will try to understand the difference between MLP and CBOW. So MLP, we know that it is the objective function is basically MSC, that is mean square error. But in CBOW, it is basically a negative log likelihood of a word that is given in a set of context, right? So log P WO by WI, right? So what is this basically means, like this is equal to exponential of this. So what is this WO means? WO is nothing but the output word divided by, and WI means the context words, right? So here we will be getting the gradient, right? So that is with respect to the hidden output weights and input hidden weights. So both will be different because MLP has sigmoid activations, but CBOW has linear activations, right? So MLP has sigmoid activations, but CBOW has linear activation. So the method, everything is almost the same. So the advantages of CBOW is it is probabilistic in nature, and it is supposed to perform superior to the deterministic methods, and its memory is low, and it does not, since its memory is low, it does not require huge RAM requirements and all, like a co-occurrence matrix, because it need to store 3 huge matrices, right? So what are the advantages of CBOW? It takes the average of the context of a word. And say, for example, ample, it can be a fruit or a company, but CBOW takes an average of both contexts and places, and places it in between a cluster for fruits and companies. So training a CBOW from scratch can take it forever if not properly optimized, right? So the next one is about the skip-gram model. So it also follows the same, almost similar to CBOW, but there is just a flip on the architecture. Here it is to predict the context given a word. So a word is given, it tries to predict the context. So say same corpus will be taken, and using that we build like what we are going to take the same corpus that we build CBOW. Hey, this is sample corpus using only one context word, right? So here you can see that the output context one, what are you getting? This, right? This, and then here, hey, right? This I have written, and then this is being hey, right? Again, this is sample corpus using only one context, right? So let us try to understand what this is. So here the input vector for skip-gram is going to be similar to one context CBOW model. And here the calculations are up to hidden layer activations are going to be the same. So what is the difference here? The difference will be the target variable. So we have defined a context window of 1 on both sides. So there will be only 2 one-hot encoded target variables and 2 corresponding outputs. It can be seen by the, it can be easily seen, right? So 2 separate errors are calculated with respect to the 2 target variables, and the 2 error vectors, are obtained element wise to obtain a final vector, which is propagated back to update the weights, right? So the weights between the input and the hidden layers are taken as the word vector representation after training. So the loss function is going to be the same as CBOW model, right? So in case if you want to understand it better, you can look into this matrix style structure. So let us try to break down this image. You can see an input image of size 1 cross V, input hidden weight matrix of size V cross N, which is nothing but the number of neurons in the hidden layer N, and hidden output weight matrix size N cross V, right? So the output layer will be C of 1 cross V. So here we can say that C is the number of context words that I have taken 2, and V is going to be 10, and N is equal to 4, right? N is equal to 4. Hope it is clear. So now here the row in the red, right? So this is the hidden activation corresponding to the input one hot encoded vector. So it is basically the corresponding row of input hidden matrix copied. So the yellow matrix is the weight between the hidden layer and the output layer, right? The blue matrix is obtained by the matrix multiplication of hidden activation and the hidden output weight. So there will be 2 rows calculated for 2 target words. So each row of the blue matrix is converted into its softmax probabilities individually, like green box, right? So the gray matrix contains the one hot encoded vectors of the 2 context words that is target, right? So the error is calculated by subtracting the first row of the gray matrix from the first row of the green matrix, right? And it could be done element wise. So this is repeated for the next row. So therefore, n target context words we will be having n error vectors. So element wise sum is taken over all the error vectors to obtain a final error model. So this error vector is propagated back to update the weights, right? So the skip-gram model can capture two semantics for a single word. Basically, it will try to have a two vector representations of apple. One is for the Apple company and the other one is for the product. And the next one is skip-gram with a negative subsampling outperforms every other method generally. So basically, like this CBOW and skipgram are really very important to understand because these concepts are really important. So the word embeddings or word vectors are basically the numerical representations of contextual similarities between words. So how it will work is like it will be finding the degree of similarity between two words and it will be finding the odd one out, right? It will be finding the odd one out and say that model doesn't match. And amazing things like is like we will be seeing this women plus king minus man, so that it will identify and tell us that it is a queen. And probability of a text under the model also it will give, right? So it can also be used for machine translation, right? So I hope this is clear to you. This is clear to you, right? We have seen word to vec, CBOW, and basically Ngram model. And I hope you really enjoyed this session. Hello, everyone. In this video, let us try to understand POS tagging. So you may be wondering, what is this POS basically? Yeah, we have studied this in school and we called it as parts of speech. I hope now you remember that, right? So what is parts of speech and why should we understand that? Okay, so let me tell you that we are basically doing natural language processing, which is completely related to what is that, unstructured data, right? So which is completely related to unstructured data, right? So here what we are trying to do here is basically parts of speech tagging, right? So let us understand what is POS, right? So say for example, just think about a sentence in your mind, right? Now think another sentence now, another sentence now. So how do we frame a sentence, right? So have you ever stopped to think how we structure phrases? They are not random choices of words. See, I asked you to think about a statement. It was not just a random choice of words, right? So when you thought about a sentence, you actually followed some structure, right? So that it gives a proper reasoning or meaning to the phrase, right? Say, for example, we follow some cultural conventions from childhood. So like after that, what happened? Like it might have changed with respect to the region or the background, right? So with respect to the region or the background. So however, inside one language, there are certain rules like what is correct or what is not correct, right? Say, for example, in English, what I can say is there is a rule. There is a rule that adjectives are more commonly positioned before noun, right? So adjectives are positioned before the noun. So what I try to say over here, let me write something now. Say, for example, hot sun. So what does this basically mean? Sun is a noun and hot is an adjective, right? So always we place the adjectives before the noun. Yes. So what are verbs? We have studied about verbs also, right? So verbs are words that denote actions and which have to exist in a phrase, right? So verbs are words that denote actions. So dancing or singing or whatever it is, right? So that is also always there, right? So basically these rules are called as syntax. Okay, so whatever the rules, what we said was basically a syntax. So according to Wikipedia, it is basically the set of rules, principles and processes that govern the structure of sentences, right? So now if you are wondering a grammar, so what is meant by grammar? Grammar is basically which is equal to no syntax plus phonology, right? Plus morphology, like so syntax plus phonology plus morphology, right? So these contains all the types of important rules of a written language, right? So let us try to understand this. Say, for example, if we have to, so now let me tell you what is parts of speech, right? So part of speech tagging is the process of assigning different labels known as POS tags to the words in a sentence. So that tells us about the part of speech of the word, right? So there are basically two types of POS tag. One is universal tag and another one is detailed POS tags that we will see. So I'm here again and again saying about syntax, right? So what is meant by syntax? Syntax is nothing but it is a set of rules, it is a set of principles and processes that govern the structure of sentences in a given language, and it is usually including word order, right? So like for example, to better be able to predict these rules, it is being defined that like words belong to classes according to the rule they assume in the phrase, right? So these roles are the things called parts of speech. So there could be number of distinct roles that may vary from school to school. So there are, say, for example, most of the times we give importance to those 8 rules, basically. That is what we have studied in the school, right? So that we will see. So parts of speech tags have a large number of applications because in case if you study something, you should know why I am studying it, and what is the purpose of it, right? So why is it really required? It is really required for text cleaning, feature engineering task, and the third one is about word sense disambiguation, right? So text cleaning, feature engineering task, word sense disambiguation. So let us try to analyze 2 sentences now. So the first sentence is like, please book my flight for New York. And the second sentence is that I like to read a book on New York, right? So sentence 1, please book my flight for New York. And the second sentence is that I like to read a book on New York, right? So here again, you can see that book and book. Do you think that both are same meanings? So this is what I was telling about this word sense ambiguities, right? So here it is saying that please book my flight. But this is basically a book. Book in the sense it is going to be noun. This is basically a verb, right? So based upon the sentences, it is basically changing, right? So this is what, this is why we are giving more importance to the syntax, right? Hope this is clear, right? Now let us understand, just like that I wanted to show you like what are these parts of speech and all. You can see that basically an adjective, adverb, article, pronoun, conjunction, noun, preposition, and verb, right? So let us try to understand what is that, right? So when we talk about adjective, it could be something like a beautiful, a green, wonderful, awesome, right? So, right, so this is basically adjective. And when we talk about the adverb, it could be like hardly, above, sorry, soon, which is basically explaining about the verb, right? So the next one is about article. Article means and the, right? So the next one is about pronoun. Pronoun in the one is the one that is explaining about the noun, basically. It could be it, he, or she, you, like that, right? So the next one is about conjunction. Conjunction is just, it acts like a bridge in the sentence. So it could be like and, or but, or it. And the next one is about noun, right? So the next one is about noun. What is noun in the sense, like I can say that it could be anything like a cat, apple, guitar, violin, or it could be spoon, something like that, right? So the next one is about preposition. Preposition is nothing but to, with, in, and all, right? So the next one is about verb. Verb we know, right? So what is basically the verb, right? Like working, stood, ran. So all these things are basically verb, right? So now let us try to understand the methods of POS tagging. So before that, let me tell you, like when you consider NLP, it is also common to consider there are some other there are some other classes like determiners, numerals, right? Numerals and then punctuation, right? Determiners, numerals, and then punctuation. And there are also some deeper variations of these main classes like proper nouns and present tense, past tense, all those kind of stuffs, right? So in current day NLP, like there are two tag sets that are commonly used to classify the parts of speech of a word. Like it could be universal dependencies tag set. Simply we call it as it is being done by Spacey, and the second one is pen tree bank tag set. So that is being used by NLTK, right? So ultimately, what POS tagging means is assigning the correct POS tag to each word in a sentence, right? So today it is no, more commonly done using automated methods. So let's try to understand how useful it is, right? So people ask this question like when and why we use POS tagging, right? So so you want to know what are the qualities of a product in a review. So one way is that you can extract only the adjectives into the review, because when you extract only the adjectives, it could be like good or bad, something like that, right? Also, you could use these words to evaluate the sentiment of the review, right? So this is one of the applications of POS tagging, right? And then as mentioned, the POS of a word is important to properly obtain the word's lemma, right? So this is basically the canonical form of a word. So for example, what is the canonical form of living? To live or living, right? So it is basically, it depends upon semantically on the context and syntactically on the POS of living. So if living is an adjective, like in living room, right? So we have base form living. If it is a noun, it could be he does it for living. So, but if it is a verb, he has been living here. It is to live. These are the example, right? So this is where the POS matters. So considering, see, what I try to say over here is when I say living, it could be like a to live, it could be living, it could be living, so it could be adjective, it could be verb, sorry, it could be noun, it could be noun, it could be noun, it could be verb, right? Fine. So considering all these cases, then use POS tagging when there is a need to normalize the text in more intelligent manner, right? So another use is to make some handmade rules for semantic relation extraction, like attempting to find actor, like a noun or proper noun, action, and modifiers based on this POS tags, right? So how it can be done? So now we have to understand how it can be done. So in case if you read out any articles on stemming and you have no experience in the area, then you might be frightened by the idea of creating a huge set of rules to decide whether a word is this or that POS, right? So while so sometimes like let me explain this way. Basically, like I'm saying that we have to do POS tagging basically to do certain tasks like sentiment analysis or whatever it is, right? So in this case, there may be a question like how we can do this POS tagging. So it can be done in several ways, like a manual tagging, rule-based tagging, stochastic or probabilistic methods, and the fourth one is deep learning methods, right? So first, let us try to understand rule-based tagging, right? Rule-based tagging. What is this? So before that, let me explain what is manual tagging, right? So say, for example, in the schools, what we have done, we have this parts of speech sentences that is being given as the homework, or the teacher may teach in the class, and we used to sit and manually connect with that, like what is verb, what is noun, what is adjective, right? So that is basically manual tagging. So what is the problem here is this is time consuming because this is a non-automated method. Right. So the next one is about rule-based tagging. So this is the first automated way to do tagging, right? So it consists of a series of rules basically. So it can be done by a specialist and it can easily get complicated, right? So here here if you look into this, this basically use dictionary or lexicon for getting possible tags, okay, for tagging each word. So if the word has more than one possible tag, then rule-based taggers use handwritten rules to identify the correct tag. So disambiguation can also be performed in rule-based tagging by analyzing the linguistic features of a word along with its along with its preceding, right? So this is what you have to understand over here, right? So this is basically the rule-based tagging, right? So we have seen basically the first part about what uh, manual tagging. Now we are trying to understand what is this rule-based tagging, right? So the next one is about stochastic POS tagging. So this is basically in stochastic based model. What I can say is it is an automated way to assign a POS to word based on the probability that a word belongs to a particular tag, or it could be based on the probability of a word being a tag based on a sequence of preceding or succeeding words, right? So these are preferred, most used and most successful methods so far, right? So they are actually also the simple one to implement. So again, here there could be two types. One is automated probabilistic methods, the discriminative probabilistic classifier like logistic regression, SVM, conditional random field, and the next one is generative probabilistic classifiers. So the examples are naive Bayes, hidden Markov models, etc. Right? So the properties of stochastic POS tagging is these taggers are knowledge-driven taggers. The rules in rule-based POS tagging are built manually, and here the information is coded in the form of rules. So we have some limited number of rules, approximately around 1,000, and smoothing and language modeling is defined explicitly in rule-based taggers, right? So when we talk about transformation-based tags, so this is the next one. Transformation based tag. So like if you compare the similarity between rule based and transformation tagger, then like rule based, it is also based upon the rules what specify what tags need to be assigned to what words, right? So the similarity between the stochastic and transformation tagger then like a stochastic. So it is basically a machine learning technique in which rules are automatically induced from data, right? So here how it is being proceeded, it is started with a solution, then the most beneficial transformation chosen, and then it is being applied to the problem. Say, for example, start with a solution. So this transformation based learning usually starts with some solution to the problem, and it works in cycles. And then when we talk about this beneficial transformation chosen, in each and every cycle, this transformation based learning, it will choose the most beneficial transformation and then applying to the problem. So it is basically the transformation chosen in the last step. It will be applied to the problem, right? So the next one is about the deep learning method. So here we have to first download a corpus, and then so first let me tell you what is this basically. Methods that we use that use deep learning techniques to infer POS tags. So far these methods have not shown to be superior to stochastic or probabilistic methods in POS tagging. So it is at most at the same level of accuracy at the cost of more complexity or the training time, right? So these results are thanks to the further development of stochastic or probabilistic methods, so which are mostly done using supervised machine learning techniques. Okay, so I'll try to I'll try to offer the most common and simpler way to POS tag. So for doing that, how these steps can be done, right? So first download a corpus. first download a corpus. So a corpus is how we call a data set in NLP, right? So we may use pen tree bank sample from NLTK and universal dependencies corpus, right? So the second step is that we have to extract the features from the words. So we do that by getting word termination or preceding word or checking for hyphens, etc., right? So this will compose the feature set which is used to predict the POS tag. Then the third step is that we load and train a machine learning algorithm. We will use a conditional random field suit that it is compatible with the sklearn. So the most used machine learning module in Python. Then we test the trained models. Then we check the F1 scores for each one. So we actually provide a way to test the models in a more practical manner, right? Then we save the models to be able to use them in our algorithm, right? So the next one is about POS tag, right? So again, the same point, we are going to understand this in detail basically. So the first type of grammar is constituency grammar. So what is meant by constituent in the sense any word or group of words or phrase that can be termed as constituents, right? So the goal of this constituent grammar is to organize the sentence into its constituents using certain properties. So these properties are driven by a speech tag or noun or verb phrase identification. Say, for example, constituency grammar can define any sentence that can be organized into three constituents like subject, context, or object, right? Clear with that, right? So say, for example, constituency grammar can define that any sentence can be organized into three constituents. This is being really important to understand a subject, context, or an object, right? So these constituents can take different values and accordingly it can take different sentences, right? So the cats, the dogs, see, let me tell you what that means basically. So when I say that the cats and I'm saying that are running and then I'm writing in the park. Okay, so let us try to understand basically this is being the subject and this I can say that this could be the context and this is the object, right? So another way to look at the constituency grammar is to define that in terms of parts of speech tag, say a grammar structure containing a determiner, noun, adjective, verb, preposition, determiner, noun, right? So this corresponds to the same sentence. So like in case if you write the same sentence like the cats are running in the park, so we can say that this is basically noun, right? This is basically the noun and this running is basically the verb. And here what is happening in the park, right? So in the park is again going to be noun, right? So this is what we are dealing with this, right? So the next one is about dependency grammar. Next one is about the dependency grammar, right? Right. So when we talk about dependency grammar, we can also have different type of grammar. That's basically dependency grammar. Say, for example, in the same dog, we are taking like a barking dog, right? And the dog was modified by barking as the dependency adjective modifier exists between the two. So basically what is happening here, dependency grammar organizes the words of a sentence according to their dependency. So one of the word is taken as a one of the word is being taken as the root, right? One of the word is being taken as the root and all the other words are directly or indirectly linked to the root using their dependencies, right? So these dependencies represent the relationship among the words in a sentence, right? So it is basically to understand the structure and semantic dependencies between the words, right? We will look into this in detail, right? So now let us try to understand the next one. So when we talk about this parts of speech, like these tags are used in universal dependencies, a project that is developing cross-linguistically consistent tree bank annotation for many languages, right? So these tags are based on the type of word. So example, noun, that's common noun, adjective, adverb, right? Right, fine. And so another way to look at constituency grammar is to define them in terms of parts of speech tag, say a grammar structure containing, as I said, determiner, adjective, verb, preposition, determiner, right? So this is what you can see about this universal POS tags like adjective, adverb, adposition. So I think this is reverse, auxiliary, coordinating conjunction, determiner, interjection, noun, numeral, particle, and pronoun, proper noun, punctuation, subordinating conjunction, symbol, verb, and others, right? So when we talk about this detailed POS tags, so here these are the result of division of universal POS tags into various tags like NNS for common plural noun and NN for the singular common noun compared to noun for common nouns in English, right? So these tags are language specific, right? Fine. So now we understand that why we study about POS tags basically, and we also know what is POS tagging and how POS tagging is being done, right? So let me show some examples. Like, so you can look into this above example, IT, right? So PRON, took, verb, me, pronoun, more, adjective, than SCONJ, to NUM. NUM means it is basically a number, numerical, right? So has, noun, and to is particle, translate, verb, right? So these all things are given. So the next one is about dependency parsing. So what is this dependency parsing? It is the process of analyzing the grammatical structure of a sentence based upon the dependencies between the words in the sentence. So how can I understand this? In dependency parsing, like there are various tags that represent the relationship between two words in a sentence, right? So these tags are dependency tag. Say for example, in the phrase rainy weather, right? A rainy weather. Here the word rainy modifies the meaning of a noun weather, right? So therefore, a dependency exists from the weather, rainy in which a weather acts as the head and the rainy acts as dependent or child. So this dependency is represented as AMOD tag, which stands for the adjectival modifier, right? So how we can understand this is, see, there could be many exists. See, when we talk about rainy and weather, we could see some dependency, right? So similar to this, there exists many dependency among words in a sentence, but what you have to note down is a dependency involves only two words, in which one acts as the head and the other acts as the child. So as of now, there are 37 universal dependency relations, right? Like how to write down in the sentence, like import spacey. So NLP equal to spacey dot load, and text is equal to then for token in NLP. And then here I have written. So basically I can use spacey for this, right? So if you look into this one, what you can see is like a dip underscore, right? So this returns the dependency tag for a word, and the head dot text returns the respective head word, right? So if you notice here in this basically the word, so in case if I give a word took over here, it has a dependency tag of root. So this tag is assigned to the word in which it acts as a head in some head of many words in a sentence, but it is not a child of any other word, right? So generally, it is basically the main verb of a sentence to, similar to took in this case, right? So the next one is about dependency parsing. Like here you can see some arrows, right? So basically these arrows represent the dependency between two words, in which the word at the arrowhead is the child, right? So this is the child, and the word at the end of the arrow is head, right? Arrowhead is basically the child and this one, right? So the root word can act as the head of multiple words in a sentence, but it's not a child of any other word. So the same example took, if I take, it has multiple outgoing arrows but none incoming, right? So therefore it is the root word. So one interesting thing about the root word is that you start tracing the dependencies in a sentence, you can reach the root word no matter from which word you start, right? So the next one is there actually the constituency parsing. That is the process of analyzing the sentences by breaking it into sub phrases, also known as constituents, right? So let me give you a small introduction about that also. This may be looking like this, right? So when we talk about this one, so you could have seen some features like this, right? Say for example, it's going to be like okay, let me tell you. So it's going to be like NP, right? You might have seen this in the internet, basically PRP, and this is going to be it. So in case, so here the words of the sentence, so here you can see that, say for example, here the first one I have written it, right? So here the POS tag for this it is basically PRP, right? So let me tell you, see what I am trying to say here is, okay, I have written NP, that is nothing but noun phrase, and VP if I write, that is verb phrase, right? So these are basically the constituent tags. So here how it will be taken is each sentence is taken and it is assigned to certain phrasing, right? So that is basically constituent phrasing, right? So we will be studying all these stuffs in detail in the practical session. Right, hope this video in this lecture I have explained clearly about parts of speech. So some introduction part we have got. So I guess you enjoy the lecture. Thank you. Hello everyone. In this video, we are going to discuss a very important concept called named entity recognition, which we generally term it as NER. So what is this named entity recognition? So now look at this. It automatically finds names of people, places, products, and organizations in text across many languages. So you can see here like people, places, products, and organizations. So what is happening? There is a big text or a paragraph. From that, if it identifies people, places, products, organizations, etc., then the task is called as named entity recognition. So NER is a form of natural language processing. That is, it is a form of NLP, which is a subfield of AI, artificial intelligence. So what do we do in this NER? We identify and categorize key information in text. So this key information is basically called as entity, right? That is why it is being called as named entities, right? So this entity could be any word or it could be any series of words that consistently refers to the same thing. So every detected entity is classified into a predetermined category. It is not very difficult. It is an easy concept and also interesting concept, right? So named entity recognition sometimes referred to as entity chunking, extraction, or identification. So basically, it is the task of identifying and categorizing key information from the text, right? So this is what you have to know. Let us try to understand how this NER basically work. So NER model is a two-step process. So the step one is detect a named entity. Step two is categorize the entity. What is entity? I have already told you, categorizing key information, right? Fine. So what is this? How can I understand this better? Detect a named entity, which involves detecting a word or string of words that form an entity. So each word represents a token. We all know that, right? So the University of Delhi, when you say this University of Delhi, it is a string of basically 4 tokens that represent one entity, right? Fine. So the second step is that categorize the entity, right? Categorize the entity. So here, what I try to say is it is basically not 3 tokens, it is basically 4 tokens the University of Delhi, right? So these all represent one entity, right? So the second one is that categorize the entity. So this step requires the creation of entity categories. So let us see that what it is. So how do we categorize the entity in NER model? It could be person, it could be organization, it could be time, it could be location, it could be work of art, right? So when we say person, say for example, Mahatma Gandhi, it could be a name, right? Arvind is a name, Sundar Pichai is a name, right? And then when we say Google, basically it is an organization, MasterCard, Amazon or organization. And then 2016, 1424, 2 p.m. These are all examples of time. And Bangalore, Noida, Singapore, these are all locations. Hamlet, Guernica, Exelon Main ST. So these could be work of art. So this is something similar to that, right? Whenever we have a paragraph, from that it tries to extract the information, right? So basically it is information retrieval. So we can create our own entity category. Say for example, I'm working on some other task and I want to extract a few entities, right? So as per the requirement of me, as per the requirement of my task, I can recreate or I can generate my own entities, right? So as well as we provide granular rules for which entities belong to which categories in instances of ambiguity or task specific ontologies, right? Fine. So what are the applications of NER, right? What are the applications of NER? So like I can tell you clearly that this can be suited to any of the situation which is a high level overview of a large quantity of text. So we will say at a glance, if we have to understand the subject or theme of a body of text, and we can quickly group text based upon the relevance or similarity, right? So one example, what I can say is human resources. This actually we use in most of the industries, or we use, say for example, I'm hiring 2 people, but I'm receiving applications from around 1,000 people. Now, how it is possible? Is it possible to go through all the 1,000 resumes and figure out like whom I am going to call for the first level of interview? That is not possible, right? So this could help us to speed up the hiring process by summarizing the applicants' CVs, or to improve internal workflows by categorizing employee compliance and questions, right? So the second one is about customer support. So sometimes we will be receiving a lot of trouble tickets, or the lot of complaints from the customers, and there could be lots of questions. So we will be able to apply filters by using priority keywords, right? And the next one is about healthcare. It is used to improve patient care standards, and it reduce the workloads by extracting the important information from lab reports, right? And the next one is about education, right? In education, what I can say is like it can enable students and researchers to find the relevant material by summarizing papers and archive material and highlighting key terms, topics, and themes, right? Fine. And even in case if you want to search for some historical newspapers, or like in case if you want to find out certain papers that is related to particular domain, you can use this NER, right? And then the next one is about content classification. So we using this, we can surface content more easily, and we can gain insights into trends by identifying the subjects and themes of the blogs or the posts or the articles, or it could be news articles, or it could be newspapers, something, right? So the next one is about search and recommendation engines. It improves the speed and relevance of search results and recommendations by summarizing descriptive text, reviews, and discussions, right? So these are basically the applications of NER. So we may be getting a question in mind that how we can use this NER, right? So say, for example, you have a business or project that could benefit from NER. It is always better to start with NER because there are lots of open source libraries that we can get, like NLTK, Spacey, Stanford NER and all, right? So if we talk about this NLTK, Spacey, Stanford NER, each one has its own pros and cons. So we can't see that like a particular particular library is preferable for NER. So it has its own pros and cons. We need to produce a relevant labeled data set to train the model on, right? So what I try to say here is basically like we can create our own entity categories, as I told. So to learn what is and is not a relevant entity and how to categorize them, a model requires training data. So the more relevant that training data is to the task, the more accurate the model will be at completing the task, right? So everything depends upon the training basically. So once you define your entities and your categories, and then you can use these to label data and create a training data set. That is basically the named entity recognition can do this for you automatically, right? And then we can use this training data set to train an algorithm to label our text predictively. So simple, right? So this is the introduction and the explanation of named entity recognition. How to do named entity recognition using Python, right? Fine. So now you can look at the first line of code. I'm importing all the necessary packages like NLTK. NLTK is nothing but Natural Language Toolkit, which is a library and program for symbolic and statistical NLP for English written in Python programming language. And also it contains a text processing library for tokenization, parsing, classification, stemming, tagging, and semantic reasoning. And then from NLTK, I have imported this word tokenize, which is being used to tokenize the paragraph or the sentences into words. And then from NLTK.tag, I have imported POS underscore tag, which is used for parts of speech tagging. And then from NLTK, import NE underscore chunk. Chunking means it's a process of taking individual pieces of information and grouping them into larger units, right? And then I have downloaded this maxent me chunker, right? So this is the text I have taken. This is the text I have taken. European authorities fined Google a record $5.1 billion on Wednesday for abusing its power in the mobile phone market and ordered the company to alter its practices. So what I'm doing in the next step, I'm defining the pre-processing of the sent basically. So sent is equal to NLTK.word underscore tokenize sent, and sent is equal to this NLTK dot POS underscore tag send return send. So what I'm doing is I'm going to pre-process this text basically, right? So when I print out that, what is happening? Like you can see European JJ authorities, MNS, find verb, Google now. So like basically it is being tokenized, and also it is doing the part of speech tagging, right? It is doing tokenization as well as the part of speech tagging. Then I am defining a pattern over here, and then from NLTK I am using this using this regex parser, and then for this pattern, right? So this is what I'm printing out, and this is the tree. See, I can show it in this form also, right? So what I'm doing now, from NLTK.chunk import, I'm importing to basically now, and then from print import pprint, and then I'm just printing out all these things, right? Then I'm downloading all the words. I mean NLTK.download words, right? So once I do that, I'm trying to do the chunking of this already tokenized and POS tagged words, right? So this is what I'm getting. But here you can see that Google is being tagged as a noun, right? Google is being tagged as the noun, right? So what I'm doing now, I'm trying to do also with the spacey now, right? So import spacey, from spacey import displacey, from collections import counter, and import en underscore core underscore web underscore sm, and then NLP equal to this, right? So this is basically the doc I have taken, and just I'm just printing it down, so you can see the tag as well as the description over here, right? So the first token of a multi-token entity, and this is an inner token of multi-token entity, and the final token of a multi-token entity, single token entity, non-entity token, right? And then I'm just trying to get the output, right? So once I do that, what I have done is, from BS4, I have imported beautiful soap, I have imported request, I have imported RE, and then I'm defining URL to string, and then just I'm trying to get this, right? So totally I could see that length is basically 158, okay? And then what I'm trying to do is I'm trying to label it now. So when I label it, I'm getting output as person 81 and a random name. I'm saying cardinal 5, and then it could be like ordinal 1, and say product 2, date 19, right? So what I'm doing is now x dot text for x in article dot ents. So I'm trying to get the most common, right? So here I could see that this is 32, this is 17, and Trump has appeared for 13 times. And then I'm writing other sentences equal to x for x in article dot sense, and trying to print the sentence now. So this is what the sentence look like, and I'm using displacey now, displacey dot render, and NLP str sentences 10, Jupiter equal to true, style equal to int. So now you can look at over here, this is basically the person, and this house is basically the organization. So July is being tagged as the date, right? So this is what we could see. If you look into that, you cannot see any other important entities, right? So these are the three entities we could see in this sentence. So in case if I look into as an image, like you can understand, like a Mr. Suskok had testified before. So you can see that it is being tagged, right? Mr. Is being tagged, and this is being tagged, and had is being tagged. So this is what being given here. And then this is I'm trying to use all the above, like with the POS and Lima and all, and this is what I'm getting as the output, right? So then what I'm doing is I'm using dict of string x dot label for x in NLP, and then I'm trying to get that. I can get to know that this is basically a person, houses, organization, July is date, right? So what I'm doing to what I'm trying to do the same is, like with the help of this, trying to print it out. You can see that here Peter Strzok name is there, it is being tagged as person. You can see that. And here there is another name, JJ Kirkpatrick, and that is also a person. And Adam Goldman is a person. Fired Peter Strzok is a person. Trump is a person. Michael is a person. So you can see that randomly I will show you, I'll show you like wherever there is a name of a person, okay? And then you can see that, say, for example, organization, you can see that the New York Times, and right, so you can see that FBI, and no, like though you cannot expect 100% performance in any model, but it will do whatever is being possible, right? Okay, so this is what happened, and you can see that whenever there are weeks, it is being tagged as date, and 100 is being tagged in cardinal, 1 is being tagged as cardinal, over months is tagged as date, 2016 date, right? So this is what we are getting, right? So you can look into the second, we all know that, right? It is being cardinal, and army is being tagged as, no, army is being tagged as organization. clear, right? So this is how it is being done, right? So when we talk about named entity recognition, this is the most popular, no, most important questions in the interviews, because they will ask you to do like how do you proceed with the named entity recognition, right? So you must be able to do that, right? So basically it will try to tag a person, then it will try to tag NORP, which are nothing but nationalities, or it will also tag NORP, sorry, NOR. Otherwise, let me clear it up. Okay. So I can tell you that there are several things what and all named entity recognition can do is it could be related to person. We know what is person, and it could be NORP, right? NORP is nothing but nationalities or religious or political groups. It could be FAC. FAC is building, airport, highways, and all. And then ORG. ORG is companies, agencies, institutions, right? And then GPE, right? So GPE is countries, cities, states, right? And then LOC. LOC is nothing but non-GPE locations, and it could be product. Product in the sense it could be objects, vehicles, foods, etc. And event means it could be like hurricanes, storms, and also battles, wars, sports, events, right? And then law, right? Law means named documents made into laws, and any language, right? It could be language, it could be date, and it could be time, and it could be percent, right? It could be percent, it could be money, it could be quantity, right? So money in the sense it could be monetary values, including unit. And when we say quantity, it is measurement as of weight or distance. And then ordinal. Ordinal is first, second, third, etc. And cardinal, right? So these are very simple. And again, it depends upon your requirement. So basically, what words you want to, what entities you want to tag, that you can choose on your own. Accordingly, we can train the data and work on it. Hope this is clear to you. Let us discuss about text wrangling. So just we are going to look like how to use Python for text wrangling. So in all the machine learning models, we used to pre-process the data, right? So similar to that, even in NLP, it is really required to do text pre-processing, right? So let us try to understand that in detail, right? So what are the pre-processing steps, or what kind of wrangling we can do with the text data, right? So let us start it. So first I have imported NLTK. From NLTK, I have downloaded Punch, WordNet, stopwords, average perceptron tagger, right? Okay. So I have taken an example of text. Machine learning algorithms can help in converting text to numeric feature vectors, right? So when I execute this code, I'm getting the same output, because basically I'm trying to get the output of text. So when I write dot lower, so let me clear all this output now, right? So that would be really interesting, I guess. So let me clear the output. So this is basically the text. So what I'm doing now is text dot lower. So what I'm getting now, you can see that in the previous line, you can see capital M, right? Machine learning algorithm. So that is converted into lowercase. Now, when I write text dot upper, I can convert everything into uppercase letter. Text dot title, right? Text dot title. So what I'm getting, machine learning algorithms can help in converting text to numeric feature vectors. So what is the difference here? Capital M, capital L, capital A, capital C, capital H. That is what happening because we have given title, right? So this is basically about the case conversion, right? So the next one is about tokenization. What do we do in tokenization? Let us see. So this is basically the sample text I have taken. Text processing, text pre-processing is a crucial step in NLP. Cleaning our text data in order to convert it into a presentable form that is analyzable and predictable for our task is known as text pre-processing, right? So import NLTK dot send underscore tokenize sample text. So what is happening here? The first sentence is text pre-processing is a crucial step in NLP. And the second sentence is that cleaning our text data in order to convert it into a present form that is analyzable and predictable for our task is known as text pre-processing, right? So if I want to convert it into a word tokenization, now you can see that text is separate, pre-processing is another word, is another word, is another word, crucial is another word. So these are basically the tokens, right? Now I have used NLTK dot talk tokenizer, and just let me do that. Now again, what you can see is text pre-processing is a crucial step, right? So this is what we are getting. So now I have imported Spacey, and from Spacey I'm loading encode web SM. So what is that? So after that, what I'm doing is text underscore Spacey is equal to NLP sample text, right? So what is the sample text over here? Sample text is this one, right? So after that, what I'm doing, obj dot text for obj in text underscore Spacey dot sense, right? So now in the next step, what I'm doing, text underscore Spacey, right? So I hope this is clear, right? So this is what happening over here. The same thing we have done with the help of Spacey, right? So in case if I want to remove HTML tags and noise, so I have imported request and request dot get, and just I have written one URL dot text, right? So what the next step what I have done is, in the next step what I have done is I have imported RE from BS4 import beautiful soup, define strip underscore HTML underscore tags text. So soup is equal to, this is what I have written the code. Now let us execute and see what is happening over here, right? So you can see that this is basically the this is basically present in that particular URL, and this is what I'm getting. So this is the start of the Project Gutenberg ebook, the Bible King James Book 1, right? So this ebook was provided by David Whitger, right? So this is what I'm getting, book 01 Genesis, right? So now if I want to remove accented characters, I'm importing Unicode data. So define remove underscore accented underscore chars text is equal to Unicode data dot normalize nfkd dot comma text dot encode ASCII that I'm asking to ignore, and decode UTF-8 ignore, right? So let me execute this code. And for example, I have taken I have assigned some accented text to A, and let me execute this. Now you can see that this is basically accented text, right? So now in case if I want to remove this accented characters, just I'm writing remove underscore accented underscore cars, right? So what is happening now? I'm getting the output as some accented text only, right? So import RE, define remove underscore special underscore characters, text comma remove underscore digit equal to false. So basically I'm making remove underscore digits equal to false, and then I'm writing pattern also, if not remove digits else this one, right? And I'm asking it to subtract sub that pattern comma text, right? So when I do that, so I'm taking a sentence over here. Well, this was fun. See you at 7:30. What do you think, right? So now in case if I want to remove all these special characters, remove underscore special underscore characters from this, yes, basically remove underscore digits equal to true. So now you can see that I am getting only the text, I'm getting only the string, I'm not getting any special characters over here. So when I write remove underscore special underscore characters, now I'm getting the digits also. In the previous case, I have written remove underscore digits is equal to true. So I asked it to remove the digits, right? So that's the reason the digits was being removed, right? So hope it is clear, right? So this is what being done by these things. And then let us try to understand porter stemmer. From nltk.stem, import porter stemmer. So ps is equal to porter stemmer and ps.stem. I have given some examples like leaving, leaves, left. So you can see that ps.stem leaving, then ps.stem leaves, ps.stem left. So what is happening now? I'm getting output as LEAV, LEAV, LEFT. So what does this stemmer do? This provides the, or this cuts this word, and it is just reducing, I mean, it is just eliminating this ing and just giving me the output. So here the problem is LEAV doesn't have any meaning, right? So in case if I write LYING, I'm getting LIE, right? This is fine. When I write for strange, I'm getting STRANG, which doesn't carry any meaning. Sometimes what may happen is when we do stemming, it may lead us to, it may give us some word that actually has some other meaning. So those are the complications with the stemming. Now import NLTK, P is equal to NLTK dot porter stemmer, NLTK dot stem dot Lancaster stemmer that I have written in LS, and define simple underscore stemming, text comma stemmer equal to PS, and then just I have written this function, right? So when I run this and I have taken, my system keeps crashing from yesterday, okay, yesterday, or crashes, okay, presumably we are not lying, right? Okay, so let me run this now. What I'm writing now, simple underscore stemming, yes comma stemmer equal to PS. My system keeps has changed into keep, crashing has changed to crash, from yesterday, presume we are not lying, right? We are not lying, so that has changed to we are not lying. So now simple underscore stemming, yes comma stemmer equal to LS. Now what is happening? My system keep crash from yesterday. So I think I'm getting the same other than this one, right? R is changed to AR. In case if I use lemmatization, what will happen? So in lemmatization, it will take the root word which have the proper meaning. So from nltk.stem, import wordnet lemmatizer, WNL equal to wordnet lemmatizer, and help WNL dot lemmatize. So now you can see that what is happening here. Say for example, cars. Right now, car is changed to car. And when I try to lemmatize this boxes, I got the output as box. For running, I'm getting run. Ate, eat. This is brilliant, right? Because this is not possible with stemming. Ate is converted into eat. Then with the adjectives, saddest is changed to sad, fancier is changed to fancy. So the next one is about ineffective lemmatization. You can see that eight, fancier, and fancier, right? What is over here? Like what I'm trying to say is like here I'm specifying that which whether it is a noun or verb, just I have mentioned over here. Now I'm taking another, usually we use this example in all the documents. Yes is equal to, the brown foxes are quick and they are jumping over the sleeping lazy dogs. It looks funny. I'm going to tokenize it now. When I tokenize it, it is getting converted into tokens, which means the words. Now I'm going to lemmatize that. So what is happening now? The brown fox are quick, and they are jumping over the sleeping lazy dog. Now I'm using the POS tag. What I'm getting the corresponding tag for each and everything. Say for example, sleeping means sleep plus ing. Basically it is verb plus gerund, right? So this is what I'm getting. Even for jumping we are getting the same, right? So this is what we are getting. From nltk.corpus, import wordnet.adj, right? So I am getting A, right? So define POS underscore tag underscore wordnet. And for this tagged tokens I am doing, right? So when I do that, I'm getting for each and every case. What is this basically, right? We know what is what, right? So what is happening here? It is tagging with the POS, right? So you can see here, for verb, it is being written as V, and for adjective, it is being J, and adverb, noun. So everything is being denoted already here under this tag underscore map, right? So what are we getting now? I'm getting what I'm getting N basically, right? So that is what I'm getting. Sleeping is basically verb. Lazy is basically adjective, right? So this is what actually happening, right? Sorry, adverb. Lazy is basically what is that? Lazy, where is that? It is showing it as A, right? So we know that, right? Okay, fine. So the next one is about lemmatized text, and here we are for each and word tokens we are doing it. When we do that, we get the brown facts. You can see that here WNL dot lemmatize word comma tag for word comma tag in wordnet underscore token. So what is happening here? The brown fox R, right? So the R is converted into B. Quick and they are get converted into B. Jumping got converted into jump over the sleep lazy dog, right? So hope it is clear, right? So you can also try out something like this. Then WNL is equal to wordnet lemmatizer, and and here again I'm giving the lemmatizer now. So the same sentence, if I try to lemmatize underscore text of X, this is what I'm getting, right? The same thing, right? Fine. So this is what I am getting, right? Now the next one is that define remove underscore stop words. Text is underscore lower underscore case is equal to false. Stop words is equal to none, right? If there are no stop words in the sense here I have used English, right? If it is lowercase, what has to be done? Otherwise, what has to be done, right? So when I run this, then we write nltk.corpus words English, right? So this is being I, me, my, myself, we, are, ours, ourselves, you are, right? So it is showing some stop words, okay? And then in case if I ask it to remove the stop word, now what I can see, previously it was the brown foxes, right? So the is missing, the is removed, brown foxes, or right, R is being removed because it is a stop word. Quick, jumping. So over is basically a stop word that is being removed. Sleeping lazy dogs, right? So you can also try out that. So in case if you want to remove something specifically, you can do that, right? So stop underscore words dot remove the stop underscore words dot append brown. And in case if you want to remove underscore stop words, yes, the lowercase equal to false and stop words equal to stop underscore words. So what is happening now? Since I have asked this to do it, I'm getting the foxes quick jumping the sleeping lazy dogs, right? So hope this is clear to you. So this is a simple notebook which is clearly explaining about text wrangling.
NLP with sequence model. It will process some sequential data. It can be row-wise or column-wise. It is in a sequence. So machine learning models use input to provide output. Okay, so it may be in a sequence, are known as sequence model. Text streams, audio clips, video clips, time series data. Time series data means which is based on the timestamp, just like weather, sales, share market data, airlines data, train, okay, which is changing within a second and minutes, okay, time to time. So these are time-based data, okay, which is in a series. Another types of sequential data are example of sequence. Traditional machine learning assumes that data points are distributed independently and identically, but in many circumstances, such as with language, speech, and time series data, one data item depends on other. Okay, that comes before or after it, just like share market. Tomorrow, what will be the share price of for a company, and what is the for today? So it's depend on they are connected. Weathers are connected. So this type of information is also known as sequence data. Similar concept of sequencing is used in machine learning to learn from a sequence of data. RNN are also well-known methods in sequence model. That's why for numerical numbers, numerical data, we use ANN, artificial neural network. If we have image image data, so we will proceed through CNN. And if we have text-based data, so we will use RNN. The analysis of sequential data such as text, sentence, time series, and other discrete sequence, which is not continuous. Okay, discrete means not continuous. So it has some gap that is not connected. So that type of data prompted the development of sequences. So these models are better suited to handle sequential data. Okay. Whereas CNN are better suited to treat spatial data. Okay. Pixel-wise data. The crucial element to remember about sequence model is that data we are working with are no longer independently or identically distributed. That means text is a good example of sequence. Sequence and the data are reliant on another due to their sequential order. If one word is dependent on another, then we can create a sentence. If this is a sentence, if this is a sentence, so they are connected with each others. Okay. So this sequence is connected with modeling is the process. Okay. So, but if you are independently processing it, so you cannot understand that whether it is a sequence or not. But when it comes through some connecting words, so it has some meaning, has some information. Okay. We have to, these inputs values could be time series data, which shows how certain variable x, okay, x1, x2, x3, such as demand for a given product, okay, product demanding, so changes over time. So another example is because at a winter season, uh, customers are purchasing for winter clothes. Okay, so they are not buying some hot season uh, clothes. So for that, you have to understand using the data and the demand of the product, or which is changes over time. Okay, so these are time series data. The data which changes over time. Okay, it's called time series data. Just like weather, which is always changes through the time. Even a per day, in the morning the temperature are different, in the night it is different, in the noon it is different. So it's changing continuously. So another example is text prediction, in which the sequence modeling algorithm predicts the next word based on the sequence of the previous phrase. Sequence model is the process of producing a sequence of values from a set of input values. It's like temperature, ring width, ring number, magnitude, satellite data. It can be used to show how certain values such as demand for a given product changes over time. So we have to use it for text prediction for next word or the previous one, depend on the previous phrase. In other words, sequential data we can term video data. Okay. If a movie, 3 hours of movie, if you will remove 5 minutes in gap uh, of all throughout the video, you are removing 5 minutes after 10 minutes. So you cannot understand the movie because all the videos, all the images according to the time stamp. Okay, just like in a 1 second, how many frames, that means how many images are showing and how they are moving. Okay, so in a second, there are 4 images, 5 images, 10 images. If you will remove it, so you cannot understand the data. You cannot understand the story. So that's why they are connected in a sequence. All the images are connected through the sequence and some voices are binding. So the audio and video data are also sequential data. Images up to extent as sequential data. Below are a few basic examples of sequential data. These are time series data, machine translation. In time series, predicting time series such as stock market projects. Text mining and sentiment analysis are two examples of NLP. Machine translation, you are using some other language as an input and the sequential model will convert it to a different type of language. Image captioning is assessing the current action and creating a caption for the image. Deep recurrent neural network DRN for speech recognition. Deep recurrent neural network for speech recognition. Okay. So these are the you can use for music also, creating music. Okay. You had trained using Shakespeare's voices, how the Shakespeare's use uh, his voice for A, B, C, D, and using that you can create a series of combining all those words. So even different words, how the Shakespeare use, what are the pitch and the frequency or the wavelengths of that voice. So you can use those small parts of speech to train your model that it can learn through that pitches. And uh, if you will provide another text, which song is which poem are written as uh, uh, the singer was different. Okay, so it can be converted uh, of the Shakespeare voice. Okay, so AI is very creating the new type of challenges for the insecurity also because using AI you can do anything. Okay, you can render anything or original thing to artificial. Recurrent neural network for predicting transcription factor binding sites based on DNA sequence analysis. Okay, using AI, they are analyzing DNA also. How different. This is biological stuff. So if you have any ideas how the biology uh, techniques are used, so you can use them as a data. So the data can be analyzed and you can create another type of thing for mixing a lizard with a human. How the DNA can possible? What are the factors are important to creating a lizard man? That means which is totally biological. They are experimenting using AI because AI can give the recommendation and ideas which the human cannot do even in a 10 years to 50 years. Okay. It can analyze the previous all DNA data and provide in a few hours or a day. Okay.
Hello everyone. In this video, let us try to understand sequential models, and also we will get to understand more about recurrent neural networks. So have you ever wondered why do we give preference to sequences? So we all know the meaning of sequences, right? So why is really sequence required, right? Fine. So before diving deep into this recurrent neural network, we have to understand certain kind of stuffs which certain kind of stuffs which are the concepts which really require to know the proper understanding about sequences. So first, let me tell you what are recurrent neural networks. So recurrent neural networks are a class of neural networks that is powerful for modeling sequences. 1 minute. Okay. That is powerful for modeling sequence data such as time series or natural language. So what is this basically? We have a clear understanding about neural networks, right? So recurrent neural networks are also a class of neural networks that is being used for modeling sequence data. It could be time series or it could be related to natural language. Actually, what we are trying to understand here is about the natural language. And also we have a clear understanding about feed-forward neural network, right? So feed-forward neural network. So RNNs are also based on the same principles as feed-forward neural network, except that it takes care of temporal dependencies. So what are these temporal dependencies? It's very simple. In RNNs, along with the input of the current stage, it also takes care of the previous stage's input, right? And also it includes feedback and memory elements, right? So how can we understand this better? So if I give some examples to it, that could be make you to understand in a better way, right? So let me take the next one. Now look at this statement. So basically, the beauty of recurrent neural network lies in the diversity of application. See, whenever you deal with the RNNs, they have great ability to deal with the various input and output types, right? So the first one you can see that I really like the color of my new dress, right? So I really like the color of my new dress. The second sentence is that I do not really like the movie, right? So I do not really like the movie, right? So this is basically a negative statement. So that is what it means. This I like it, this I don't like it, which means this could be positive statement, this could be negative statement. So that is what I have written here. So let us try to understand what is sentiment analysis. So this is basically the task of simply classifying tweets into positive and negative sentiment. So here the input could be a tweet of varying lengths, while output is of a fixed type and size. What does this mean basically? Say, for example, I have, so just take some companies, or you are purchasing some products from a shop. It could be shop, or you can buy from Amazon or Flipkart or some companies, and there could be some forum where you may write the feedback about it, right? So the feedback could be positive feedback. You could have liked the product, or you could have not liked the product, or it could be neutral also, right? Or it could be neutral also. So why it is really essential? Should I know that whether the statement is positive or negative? Yes, we should know that, because then only I can, based upon the customer feedback only, I can develop my business, right? So the output is of a fixed type and size, in the sense it is going to be positive or negative or neutral. But the tweet, there is no, or the feedback, there are no limit. Or see, people may write with the emojis, people may write with the, people may write with the different languages, right? People may watch with the, people may, write with the different languages. There could be hashtags, special characters, everything, right? So I hope it is clear, right? So this is basically about the sentiment analysis. So now look at the next one, image captioning. So here we have an image, right? So when you look into this image, you can understand that a person riding a motorcycle, and you can see dirt over there, right? So on a dirt road. So here we have an image which we need a textual description. So we have single input, the image, and a series or sequence of words as output, right? So the image might be of a fixed size, but the output is of a description of varying lengths. Do you understand the difference? So here you can say that two are not actually, so here one animal, here one animal, here one animal. So I can see that like the animals are playing in the grass, right? And not only two, it could be three, or this image is not very clear, so it has taken these two as the dogs, right? A group of young people playing a game of frisbee. Two hockey players are fighting over the puck, right? So by looking at the image, by looking at the single input, a series or sequence of words are given as output. So the image is of fixed size, but the output is a description of varying lengths. Now look at this. Here you can see that French was the official language of the colony of French Indochina, comprising modern-day Vietnam, Laos, and Cambodia. It continues to be an administrative language in Laos and Cambodia, although its influence has waned in recent years. So if you look into this, it is so clear that it is in English. And if you look into this, this is being translated into French. So what does this basically mean? We have some text in a particular language, let's say English, and we wish to translate in French. So when you take English, English has its own semantic. It may have different length. For this, I mean, it would have different length for same sentence. So here, the inputs are of different length and outputs are of different length, right? So what I try to say here is RNNs can be used for mapping inputs to outputs. So RNN is used to map inputs to, right, output, right? This is what it is doing of various types, various lengths, and or generalized in their applications, right? So these are the tasks that these are some of the tasks that RNN can do, right? So now let us understand what are recurrent neural network. So now think that the task is to predict the next word in the sentence. Okay, next word. Say it could be, I am going to mall. Okay, so let's say the task is to predict the next word in a sentence. So now that could be tried by using MLP, right? So what happens in MLP? We have an input layer, a hidden layer, and an output layer. So the input layer receives the input. The hidden layer, there will be some activations, right? Activations are applied, and then finally we receive the output, right? So if it is a deeper network, so here what is the activation used? ReLU. So now let's think that we have a deeper network where multiple hidden layers are present. So you can see here multiple hidden layers are present, right? So here the input layer receives the input. the first hidden layer activations are applied, right? You can see the activations are applied, and then these activations are sent to the next hidden layer, and successive activations are passed through the layers so that we are getting the output. So each hidden layer, you can see different weights and biases. W1, B1, W2, B2, W3, B3, right? So each hidden layer has its own weights and biases. So each so that what will happen now, each hidden layer has own weights and activations, so everything behaves independently, right? Now the objective is to identify the relationship between the successive inputs, right? So can we supply the inputs to the hidden layers? Yes, we can do that, right? So in this case, what we observed is weights, biases of the hidden layers are different. And so each of the layer behave independently and it cannot be combined together. So if we want to combine all these hidden layers together, we should have the same weights and biases for the hidden layers, right? So now you can look over here, you can see here, like we can now combine these layers together. The weights and the biases of the hidden layers are all the same. You can see the W, B, W, B, W, B, FC1 activation, FC2 activation, FC3 activations, right? So all these hidden layers can be, so now you can see that like we have combined these layers together and the weights and the biases of all the hidden layers is the same. So all these hidden layers can be rolled together into a single recurrent layer, right? So it's like supplying the input to the hidden layer at all the time steps. Weights of the recurrent neuron would be the same since it is a single neuron now, right? So the weights will be the same because it is a single neuron, right? So a recurrent neuron stores the state of the previous input and combines with the current input, thereby preserving some relationship of the current input with the previous input, right? So how does it look like now, right? So let me give you an example now. Let's take a character level RNN, say where we have a word called hey, right? So, or it could be like hello, hey or hello. Why I'm using hello? So that I have the same letters repeated, right? So H-E, L-O, right? And just think that, or it could be hey. So let me start with hey now. So I'm providing two letters now, H-E, and I ask the network to predict the last letter. So next letter could be what? Y. So I'm asking the network to predict the last letter. So if it is going to be hello, I may give it as H-E-L-L. So I'm asking it to predict the last letter. So here the vocabulary of the task is basically here 2, here 4. So in real case scenarios, whenever we use natural language processing, the vocabularies include the words in the entire Wikipedia's database or all the words in a language, right? So how does this basically look like? How does this RNN network look like? The same thing I'm drawing now. So this could be X. What is X basically? It is the input. From this, it's being RNN, right? So you can look over here, and from here, this is Y, right? So this is nothing but output, and this is nothing but input, right? So here, this is how the structure, this is what the structure that try to identify the fifth letter in the word hello, right? So here the RNN block, you can see, right? It applies something called as a recurrence formula to the input vector and also its previous state, right? So in this case, the letter H has nothing preceding it, right? So then it take the letter E. So at the time the letter E is supplied to the, so when we give H, nothing is preceding over here. Then we give E, right? So at the time the letter E is supplied to the network, a recurrence formula is applied to the letter E and the previous state, which is the letter H. So these are known as various time steps of the input. So if at the time T, the input is E, at time T minus 1, the input was H. Do you get my point? So if at time T, the input is E, right? So at time T minus 1, what is the input? Yes, you are right. It was actually H. So the recurrence formula is applied to E and H both. So what will happen now? We get a new state. So what is the current state now? Let me write it over here. The current state is HT is equal to F HT minus 1, comma, XT, right? So what is this HT basically? HT is about the new state. HT minus 1 is the previous state. XT is the current input. So now we have a state of the previous input instead of the input itself, because the input neuron would have applied the transformations on our previous input. So each successive input is called as time step. So what's happening here? We have 4 inputs, H, E, L, L, right? We have 4 inputs to be given to the network during a recurrence formula. So the same function, same weights are applied at the network at each stage. So taking the simplest form of recurrent neural network, say in case if the activation function is tan H, the weight at the recurrent neuron would be, right. So let me write it. Like for example, if you are saying activation function as tan H, so how does it will change? HT is equal to tan H within bracket WHH. I'll explain. Just be patient. HT minus 1 plus W XH XT. Let's say the activation function is tan H. The weight at the recurrent neuron is WHH. Weight at the input neuron is WXH. And this is for the equations. We know what is HT minus 1 and HT from this, right? Fine. So the recurrent neuron in this case is just taking the immediate previous state into consideration. So for longer sequences, the equation can have multiple states. So once the final state is calculated, we can go to produce the next step, right? So this is what being mentioned over here. HT is equal to F HT minus 1 XT, right? So once the current state is calculated, we can find out the output now. So what will be the output? YT is equal to WHY and HT. So we know what is what, right? Fine. So let me summarize the step now. A single time step of the input is supplied to the network. That is XT is supplied to the network. We then calculate its current state using a combination of the current input and the previous state. That is, we calculate HT, right? The current HT becomes now we have HT, right? So the current HT becomes HT minus 1. That is for the previous state, right? HT minus 1 for the next time step. So we can go as many time steps as the problem demands and combine the information from all the previous states. So once all the time steps are completed, the final current state is used to calculate the output, right? So the output is then compared to the actual output and the error is generated. Now what will happen? There is an error. So the error is then back propagated to the network to update the weights, right? So we know about the back propagation, right? And then the network is trained. Hope it is clear, right? So let me explain everything in short once again. So whenever we handle textual data, the data is always in the form of sequences. And the order of the data is also very important. So for any given sentence, if the order of words is changed, the meaning of the sentence doesn't stay the same. Hence, sometimes there could be a change, right? So I don't say that in all the cases, but in most of the cases, there is a high possibility of changing the meaning, right? So the sentence information is stored in both the words as well as the order of the words in that particular sentence. So in any type of data, if sequential order matters, then we call it as a sequential data. Then we call it as a sequential data, right? So the traditional neural networks cannot handle sequential data. Why? Because in a neural network, for a particular task, we need to set a fixed input size at the beginning. But in sequential data, the size of the data can vary, right? So a sentence can contain 5 words, 10 words, 15 words, 20 words, or could be more than that. So we cannot configure a neural network to effectively deal with this kind of data. So even if we are dealing with the sentences with the same number of words, when we input the processed words into a neural network of some fixed input size, a neural network is not designed to pay attention to the sequence of the words. So the model will effectively learn from semantic information on the individual words, right? So, but it will fail to learn from the order of the words. So to convert textual data into a numerical format, we can input them into neural network. We must convert them into vectors. So this is what we called as one-hot encoded vectors or word vectors, right? So our textual data will turn into a sequence of vectors, which is exactly the format we need, right? So you can see here converting into word vectors. So what is over here? D, learning is hard but fun, right? So hope this is clear, right? So what we have done over here, we have converted word sequence into word vectors, right? We have converted word sequence into word vectors. So now let us understand this in detail. So whenever we have to handle the sequence data, we use sequential models, right? So the most important sequential models that we use in the industry are recurrent neural networks, that is RNN. So what do this RNN have? It has RNNs essentially consider the information of each element of the sequence, as well as the information of all the elements in the sequence before that particular element. So essentially, you can see that there are two input layers, one for the current word, okay, one for the current word, and the other one for the accumulated information of all the previous words, right? So essentially, RNN have two input layers, one for the current word being fed into RNN, and one for the accumulated information of accumulated information of all the previous words, right? So essentially, this is very important, right? So you can see the primary output containing relevant prediction, which we are training the RNN for. So we usually ignore the output until all the words have been fed into RNN, right? So the other output is meant to represent all the accumulated information of the words which have been input into the RNN so far, right? So let us try to understand, right? So what do we do over here? Feed the first word into RNN's first input, right? So feed the what we do over here is we feed the first word into RNN's first input. Since this is the first word, there will be no previous information. So as we have seen in the hello, right? So there is nothing. So here we are talking about the words basically, right? So we will be feed 0 to the second input. So now at this stage, the RNN will output the accumulated information of that word and a primary output. So we usually ignore the primary output of the RNN until all the words of the sentence have been fed into RNN. Then what do? We feed the second word into RNN's first input and the accumulated information into the second input of the RNN. Now what will happen? the RNN will output the accumulated information gain, right? So now this time it will contain both the first word and the second word. This is how the process will be continued until all the words have been fed into RNN, and we check the primary output of the RNN to get the prediction regarding the sentence, right? So the accumulated information keeps getting updated to the RNN processes each word. So the RNN the RNN uses the accumulated information between each step as a kind of memory. So this is what I told, right? Whenever we deal with a sequential, like this point, we have to remember always memory functionality so that it remembers all the words it has processed before. So at the final step, the RNN has essentially processed all the words in the sequence in the exact order which is required, right? So the accumulated information is passed between steps, which is called the state of the RNN, right? So the state means, so whenever we say state, this is essentially a vector of numbers, which is passed between the output of previous step to the input of the next step. So what is this basically? So here I told about state, right? So state means it is just going to be the numbers that is being passed between the output of the previous step and the input of the next step. So when the RNNs, as the RNNs get trained, it will learn to modify the state, right? It will try to modify the state such that it can derive the relevant information about the words it has processed and in the order in which they are processed. So ordering matters over here, right? So that's what I try to say. So the state, the accumulated information in the RNN essentially gives the memory capabilities. Memory capabilities means nothing, right? Hello. So when you give hello, it doesn't have any preceding. I am. So when I say I, this hello is also taken into account. That's what it means, right? So memory capability, so that it knows all the words it has processed so far, as well as the order in which they are processed, right? So this is how the inner functioning of this is how the inner functioning of this is how the inner functioning of RNN looks like. You can see that. Okay, so let me explain everything clearly, so that would be really helpful for you to understand. Let me take the pen. Okay, firstly, the current word nth, right? So I'm giving current word nth, right? So this is what you can see, word at nth position. So the current word nth is multiplied with a W1, right? Which is a weight matrix, right? Which is a weight matrix, in the RNN. Now the previous state of the n minus 1, that is being multiplied with the word W2. So another weight matrix in the RNN. So the result and output vectors are all being added. Now this added vector is then passed through an activation function. So why this is being passed through activation function? So that we can add non-linearity, right? So that we can add non-linearity to that model, right? So we can use tan H activation function for RNN. So after the activation function, we have got the new state now, right? After the activation function, we will be getting the new state now. Now the new state is being multiplied with this W3, another weight matrix, to get the final output of the RNN. So the final output is disregarded until all the words have been processed by RNN, right? So I hope this is clear, right? So this is what being given over here, right? So we should have a clear idea about it, right? So first the current word is multiplied with a W1, then the previous state is multiplied with a W2, and then this get added. Then we apply to activation function. After activation function, new state is multiplied with a W3, and finally we get the output. So in the case of sequential model, see, please understand this part actually. Since we are feeding the sequence of words into the RNN, the state gets updated for each word being input. So as a result, the state represents the representation of the words which have been processed so far. And since the state gets updated in a sequential manner, so the state will also contain information about the order of the words as well as the order themselves. So say for example, I'm saying something like, okay, I love statistics. Okay, so just if you take this example, let's consider the states at each step as the RNNs processing this sentence, right? So when I is fed to RNN, the state contains a representation of just the word I. Then we feed love, right? And when I feed this love into RNN, it will update the state which had a representation of just I love, right? As the RNN continues to get the words from the sequence, the final state representation of I love statistics. So this is how it is being working, right? So the final state of the RNN contains both the semantic information of the words in the sentence as well as the sequential information of regarding the order of the words, right? So and now we have seen how RNN predicts. Once we feed a sequence of words, let's look into how the RNN trains, right? So this is what we are going to see, right? So let's say how to train RNN for a sentiment analysis. So in sentiment analysis, we are given a sentence and we need to predict the sentiment polarity of the sentence. So the output will be either 1, if it is 1, it's going to be positive polarity, or if it is going to be 0, then it is going to be negative polarity. So this is basically a text classification task, right? So let me tell you that NLP is very difficult. Okay, so I'm writing a sentence over here. NLP is very difficult, right? This food is awesome, right? So let me write few sentences like this. So now if you look into this, what will happen? Now the data set has a list of sentences, and they say, for example, I'm getting some sentiments also, like NLP is very difficult. It is giving me negative, which is 0. And this food is awesome, I'm getting positive 1, right? So when I have these set of sentences, their corresponding sentiment scores, we need to train a RNN to give the corresponding sentiment score of a sentence after we feed these sentences to the RNN. So in the case of sequential model, the model is being used multiple times instead of once, like a traditional neural network. Say if there are 5 sentences, 5 words in a sentence, RNN will be taking values from the input to the output for a total of 5 times. So because of this, the back propagation will happen multiple times for a single training sample instead of once. So the back propagation will happen over all the steps, and the RNN has taken, and this is basically called as a back propagation through time, right? So initially, before the training process happens, we randomly initialize all the 3 weight matrices in the RNN, like W1, W2, and W3. Then we start feeding the data into RNN, right? So for a single training sample, we feed the entire sentence into RNN, and then we compare the output of RNN with the target output corresponding to the sentence, so that we calculate the loss, right? We have idea about it, right, for that training sample. So here, since in this problem, we are just doing positive or negative, so it is basically, we are using a binary classification problem. So we can go ahead with a binary cross entropy loss function. Then we backpropagate the loss function through all the steps of the RNN from the last word to the first word, right? So this is how this explains the training process for a single training example in the data set. So now when we keep on training the RNN with all the data in the data set, when it happens for multiple iterations, it will learn how to understand semantic information in each word, and also the sequential information in the way the words are ordered to successfully predict the sentiment from the sentence. Okay, now whenever we study something, there could be some problems or limitations with that particular network also. So what are the limitations here? RNNs are definitely better than the traditional neural networks at processing sequential information, but still there are some problems we are facing. One is about vanishing gradient problem, and the second one is about long-term dependencies. So what is meant by vanishing gradient problem? So RNNs perform well with short to medium-sized sequences, right? But when we perform back propagation, back BPTT, right? Back propagation for very long sequences, the gradients have to go through many weight matrices, right? It has to go through many weight matrices before it reaches the first few steps of the RNN. So now what will happen? The gradients will become very small, right? The gradients become very small because the weight matrices are increasing. Whenever the weight matrix is increasing, what happens to the gradients? The gradients become small. So when the gradients start vanishing, this is what called as vanishing gradients. So this is the basic problem, most common problem that we observe in deep learning when the neural network has too many layers. So in this case, it occurs fundamentally when we use an RNN with a long sequence. So it can be considered equivalent to a neural network having many layers. So we cannot effectively use RNNs when we are dealing with extremely long sequences, because RNNs weight matrices stop getting updated significantly after certain steps, right? So what are long-term dependencies? In sentences, sometimes the semantic links between certain words could be far apart, right? So consider, I have given a sentence like deep learning is an upcoming field in today's technology, but it is very hard. So here you can see that hard refers to deep learning, but these are very far apart. Deep learning is over here, hard is at the end of the sentence. So it is too far apart, right? So in RNN, since the state updation happens at every step, it is very hard for it to capture the semantic patterns between the words which are very far apart, right? So by the time the RNN reaches the word hard, it would not be considering deep learning as much as the recent words it has processed. Even if you give the RNN lots of training examples with a long-term dependencies, the architecture limits the ability of RNNs to capture long-term dependencies, right? So in a deep NLP, researchers have come up with better sequential models which solve the problems effectively, like LSTMs and GRUs, right? So these are more advanced sequential models. Hello, everyone. In this video, let us discuss about long short-term memory, which is in short called as LSTM, right? So LSTM is an advanced RNN. So it is an advanced recurrent neural network, a sequential network that allows information to persist. So what we have seen in RNN is like it has some limitation or some problem on vanishing gradient, right? So this is what we have seen. Vanishing gradient problem it has got. So in long short term memory, it is capable of handling the vanishing gradient problem. So a recurrent neural network is used for persistent memory. Say, for example, you are looking into some video, you are watching a movie. So you may remember the previous scene, right? Or else just think that you are reading a book, but you remember the terms that you have studied in the earlier chapter, right? So accordingly, RNNs work. They remember the previous information and use it for processing the current input, right? But the shortcoming of RNN is that they can remember long-term dependencies due to vanishing gradient. So LSTMs are explicitly designed to avoid long-term dependency problem, right? So let us try to understand what long short-term memory is, right? So it is usually just called as LSTMs. It is a special kind of RNN capable of learning long-term dependency. So they work tremendously well on a large variety of problems, and it is being widely used, right? So it is explicitly to avoid the long-term dependency problem. So remembering information for a long period of time is practically their default behavior, not something they struggle to learn. Okay. So now look at this. Let us discuss about the LSTM architecture. So at high level, LSTM also works something similar to RNN cell. Here, it is the internal functioning of the LSTM network, right? So the LSTM consists of three parts. You can see 1, 2, and 3. The LSTM consists of three parts, and each part shows an individual function. So the first part chooses whether the information coming from the previous timestamp is to be remembered or is irrelevant. So what this do is it will choose whether the information from the previous timestamp is to be remembered or is irrelevant and can be forgotten, right? So in the second part, the cell tries to learn new information. So in the second part, what you can see is it can, no, right? So it can try to, 1 minute, okay, fine. So it will try to add a new information, right? So the third one is that like there is a third part that is basically the output gate, right? So this is basically the output. So here what will happen is the cell passes the update information from the current timestamp to the next timestamp, right? So hope this is clear, right? So the part 1, forget irrelevant information. Part 2, add or update new information. Part 3, pass and updated information, right? Fine. So let me tell you, these 3 parts, we call it as gates. The first part, we call it as forget gate, right? We call it as forget gate. And the second part is known as the input gate. And the last one is called as the output gate. So like simple RNN, LSTM also has some hidden state. So that LSTM also has a hidden state where HT minus 1. So it represents the hidden state of the previous timestamp and HT is the hidden state of the current timestamp, right? So in addition to that, LSTM also have a cell state that is represented as CT minus 1 CT. So just remember, so LSTM also have hidden state for the previous timestamp on the and the current timestamp, and also it has cell state for previous as well as the current timestamp. Okay, so now look at this, right? So here you can see that long-term memory CT minus 1, HT minus 1, CT and HT. This is what I was telling, right? So you can see here HT minus 1 hidden state of previous timestamp, and this HT is basically for the current stamp, and this is for cell, right? So the cell state basically carries the information along with the timestamps. Okay, so here the hidden stamp is basically known as short-term memory, and the cell is called a cell state is known as long-term memory. So this hidden state, no, HT minus 1, HT, the hidden states are called as short-term memory, and the cell states are called as long-term memory, right? So the cell state carries the information along with the timestamp, right? So let us try to understand how this basically works, right? So this is what we have to understand. So let me write some example. So Alex is a good person, right? So this is one sentence, and also I'm adding with that like okay, Harry on the other hand is evil. Okay, so it is the sentence, right? So let us try to understand how the sentence basically works. So we have 2 sentences here separated by a full stop, right? So the first sentence says that Alex is a nice person, and the second sentence is that Harry on the other hand is evil. So it's very clear that in the first sentence we are talking about Alex, and in the second step we are talking about Harry. So as we move from the first sentence to the second sentence, our network should realize that there are no more talking about Alex, right? Because now our subject is basically Harry, right? So here the forget gate of the networks allows it to forget about it. Hope I'm clear, right? So this is what we have to understand about the forget gate. So in the cell of the LSTM network, the first step is to decide whether we should keep the information from the previous timestamp or forget it. Whether we should keep the information or we have to forget it, right? So this is basically the equation of the forget gate, right? So FT is equal to sigma XT into UF plus HT minus 1 into WF, right? So what is this XT? XT is nothing but input to, this is T, right? So input to current timestamp, right? So current timestamp. So what is this UF? UF is nothing but weight associated with that, associated with the input, right? So what is HT minus 1? So again, this is going to be the hidden state, right? T minus 1, right? So hidden state of the previous timestamp, right? Hidden state of the previous timestamp, right? So what is this WF going to be? This is the weight matrix, right? So what is WF? This is the weight matrix associated with the hidden state, right? So now I hope this is clear, right? So what does this forget gate do? It decide whether we should keep the information from the previous timestamp or forget it, right? So then the sigmoid function is applied on it. Now we know about sigmoid, right? So what does this sigmoid function basically do? It will fit a number between 0 to 1, right? So already we got FT, right? In forget gate, we are getting output as FT, right? So now this FT is being multiplied with the cell state of the previous timestamp. So we got FT. This is being multiplied with the cell state of the previous timestamp, right? So we get CT minus 1 into FT, right? So like this is what we are getting. If this is equal to 0, if FT is equal to 0, forget everything. And if it is equal to CT minus 1, if FT is equal to 1, forget nothing, right? So if FT is 0, then the network will forget everything. And if the value of FT is 1, it will forget nothing. So the first sentence we were talking about Alex, and after a full stop, the network will encounter Hari. In an ideal case, the network should forget about Alex, right? So the next one, right? So the next one is about the input gate, right? So let us look into the input gate now. Okay. So now let me write another example, like Alex knows swimming. He told me over the phone that he served the Navy for 3 long years. Okay, so let us try to understand. So in both these sentences, we are talking about Alex. So both give different kind of information. So the first sentence is telling me that he knows swimming. And in the second sentence, it is saying that like he served the Navy for 3 long years, right? So both give different kinds of information about Alex. So in the first sentence, we get the information about swimming. Second sentence, over the phone, we got to know that he served in the Navy for 4 years. So now just think about it. Based upon the context in the given first sentence, which information of the second sentence is critical? So first, he used the phone to tell, or he served in Navy, right? So in this context, it doesn't matter whether he used the phone or any other medium of communication to pass on the information. So the fact that he was in the Navy is important information and is something we want our model to remember. So this is the task of the input gate. So input gate is used to quantify the importance of the new information carried by the input. So this is the equation of the input gate. IT is equal to sigma xt into ui plus ht minus 1 into wi. So what is this xt? Xt is nothing but the input at the current timestamp, right? Fine. So what is ui? Ui is nothing but weight matrix of input, right? So what is ht minus 1? We know that it is the hidden state at the previous timestamp. So what is this wi? Wi is the weight matrix of input associated with the hidden state. So again, we have applied sigmoid function over it. So as the result of that, the value will be ranging from 0 to 1, right? So now the next one is about the new information, right? So now here, like what is being done is, see, Ni is equal to tan H, right, Xt into Uc plus Ht minus 1 into Wc, right, Wc, right? So now the new information needed to be passed to the cell state is a function of hidden state at the previous timestamp, that is t minus 1, and input x at timestamp t. So what is the activation function here? Activation function here is tan h. So what is happening now? Because of the tan h function, we will be getting the information ranging from -1 and 1. So if the value of nt is negative, right? So sorry, this is basically nt, right? So if the value of nt is negative, then the information is subtracted from the cell state. And if the value is positive, the information is added to the cell. Very simple. See, nt is negative, the information is subtracted from the cell state. If the value is positive, then the information is added to the cell state at the current timestamp, right? So the nt won't be added directly to the cell state, right? So you can, this is what previously I have written over there, and this is being the cell date now being updated. So what is happening now? Ct is equal to ft into ct minus 1 plus it into nt. So what is ct minus 1? Ct minus 1 is the cell state, right? It is the cell state at the current timestamp, sorry, and others are the values we have calculated previously. Sorry, I'm talking about CT. CT is the cell state, right? So hope it is clear. Now the next one is about the output. Now let me give you another sentence. So this is happening here, updating the cell state, right? Okay. So now let me tell you another one, right? So Alex single-handedly fought the enemy and died for his country, right? For his contributions, brave, right? So during this task, we have to complete the second sentence, right? So we have to complete this sentence basically. So now the minute we see the word brave, we know that we are talking about that person, Alex. So in the sentence, only Alex is brave. We cannot say that enemy is brave or the country is brave. So based on the current expectation, we have to give a relevant word to fill in the blank. So that word is our output, and this is the function of our output gate, right? So this is the equation of the output gate. Its value also lies between 0 and 1 because this is also a sigmoid function. Now to calculate the current hidden state, we will use OT and a tan H of the updated cell state, right? OT and tan H of the updated cell state. So what do we get now? It turns out the hidden state is a function of, so what do we get over here is, it is a function of long-term memory, right? So we get it as a function of long-term memory and the current output, right? And the current output. So if you need to take the output of the current timestamp, just apply the softmax activation function on it. So now here, the token with the maximum score in the output is the prediction, right? So this is how it looks like, right? So this is how it looks like. So you can look at the picture like so you can see that there is A and there is here A again. So this is the activation function you can see over here. Okay.
The LSTM networks in detail. So we have a clear understanding about recurrent neural networks, right? So what we have come across recurrent neural network, just let me give a recap of it. See, for example, like we are trying to, or we are watching a movie, And whenever you watch a movie, you will be remembering the last scenes, right? So what has happened actually before, right? So recurrent neural network is something related to that, right? So now what is the major problem that we faced in RNN is about the long-term dependencies, because they might be able to connect previous information to the present task, such as previous video frames might inform the understanding of the current frame. If RNNs could do this, they would be extremely useful, but can they? Right? So it depends, right? So sometimes we only need to look recent information to perform the present task. So for example, consider a language model trying to predict the next word based on the previous one. So if you are trying to predict the last word in a sentence, we don't need further context, right? So it is pretty obvious the next word what it is going to be. So in such cases where the gap between relevant information and the place that it's needed is small, so RNNs can learn to use the past information. But there are also cases where we need more context, right? Where we need more context. So consider a statement, right? I like to something like that, right? So I like, otherwise I like, and then I'm writing, I'm not writing anything, right? So, or I am writing like I speak fluent. So it could be English, it could be Spanish, it could be French, right? So the recent information suggests that. So let me make it very clear. No, like I I lived in India. So I'm writing I speak, right? I speak fluently in, right? So now this could be, when we say India, it could be of any languages, or more specifically could be Hindi, right? So recent information suggests that the next word is probably the name of a language. There is no doubt about it. It is going to be about the name of a language, right? But if we want to narrow down which language, we need the context of Hindi from further back, right? So it is entirely possible for the gap between the relevant information and the point where it is needed to become very large. So when the gap grows, RNNs become unable to learn to connect the information. So RNNs are absolutely capable of handling such long-term dependencies. A human could carefully pick parameters for them to solve toy problems of this form, right? So in practice, RNNs don't seem to be able to learn them, right? So let us try to understand this LSTM, long short-term memory networks, right? Usually called as LSTMs. These are also special kind of, this is also a special kind of RNN, which is capable of learning long-term dependencies. So it is being very popular right now. It is explicitly designed to avoid the long-term dependency problem, right? So remembering information for long period of time is practically their default behavior, not something they struggle to learn, right? So all recurrent neural network have the form of chain of repeating modules of neural network. So in standard RNNs, the repeating module will have a very simple structure. Like we have seen, like it has only tan H layer, right? But LSTMs also have chain-like structure, but the repeating module has a different structure, right? So the repeating module has a different structure. Instead of having a single neural network layer, there are actually 4 interacting a very special way, right? So we are not going to dive deep right now. So in this diagram, we will try to look everything step by step, right? So that is what we are going to do now, right? So the key, look at this one. Now let us compare this and this, right? So you can understand the difference, right? So this is basically the RNN. We had only the tan H layer, but here you could see the 3 sigmas are there and 1 tan H is there, right? So this is what we can understand, right? So here we can see that each line carries an entire vector from the output of one node to the input of others. So here you can see a pink circle, right? So this represent point-wise operations like vector addition, and the yellow box represent what is that, a network, right? Network layers. Lines merging denote concatenation. So you can see this is basically the vector transfer, this is the concatenation, and a line forking denote this is being copied, and the copies are going to different locations. So the key to LSTM is the cell state, right? Cell state, the horizontal line passing running through the top of the diagram, right? So that is what we have seen, right? I'll be showing you. So this is the cell state. This is the cell state, right? Fine. So the cell state is like a conveyor belt, right? It runs down the entire chain, right? So with only some minor linear interaction. So it is very easy for information to just flow along it unchanged, right? So the LSTM does not have the ability to remove or add information to the cell state. It is being carefully regulated by structures called gates. Okay, so the gates are a way to optionally let information out. So they are composed out of sigmoid neural net layer. That is what we have seen, right? That is what we have seen, and a pointwise multiplication operation. So the sigmoid layer, what it does, it outputs number between 0 and 1 and describing how much of each component should be let through. So value of 0 means let nothing through, right? While a value of 1 means let everything through. So an LSTM has 3 of these gates to protect and control the cell state, right? So you can see the 3 states over here, right? So now the first step in our LSTM is to decide what information we are going to throw away from the cell state. So this decision is made by the who will be taking this decision? Basically, this will be taken by the sigmoid layer, right? So called the forget gate layer, right? So this decision is made by sigmoid layer, which is called as the forget gate layer. It looks like HT minus 1 and XT, and it outputs a number between 0 and 1, right? 0 and 1 for each number in the cell state, CT minus 1, right? CT minus 1. So here, like in case if you get 1, we can say that completely keep this, or if you get 0, we may try to completely get rid of this, right? So the example, you can take a language model which is trying to predict the next word based upon the previous one. So in such problem, the cell state might include the gender of the present object, so that the correct pronouns can be used. You got my point, right? So the gender must be mentioned so that everywhere, say for example, if it is a man, everywhere it is being written like he, his, him, something like that, right? So this is what I am trying to say now, right? So when we see a new object, we want to forget the gender of the old object, right? So now this is mentioning about a man. After that, it is mentioning about a woman. So now it has to forget that man character basically. So the next step is to decide what new information we are going to store in the cell data, right? So now here there will be 2 parts. What are the 2 parts? First, there will be a sigmoid layer. First, there will be a sigmoid layer, right, called the input gate layer. It decides which values we will update. Next, a tangent layer, which creates a vector of new candidate value CT, right? So that could be added to the state. So in the next step, what we will do, we will combine these two to create an update state. So you can see over here, you can see sigma as well as tangent. So sigma, in the sense, you can see that HT minus 1 and XT, right? And for tangent, you can see that again HT minus 1 comma XT, right? So you can see that WI, WC are varying, right? So now what is happening over here? Right? So now what is happening over here? See, we have done that. Now it is now time to update the old cell state, that is CT minus 1 into the new cell state CT. right? So the previous steps already decided what to do. We just need to actually do it, right? So we have to multiply the old state by FT, forgetting the things we decided to forget earlier, right? So we decided to forget earlier. Then we add IT into CT. This is a new candidate value scaled by how much we decided to update each state value. So in the case of the language model, this is where we would actually drop the information about the old subject gender, and we can add the new information as we decided in the previous step. So finally, we need to decide what we are going to output. So this output will be based on our cell date, but will be a filtered version. So first we run a sigmoid layer, which decides what part of the cell date we are going to output. Then we put the cell state through tanh to push through the, then we are passing it to the tanh, right? To push the values to be between -1 and 1 and multiply with the output of the sigmoid gate so that we can only output the paths we decided to. So for the language model example, since it just saw an object, it might want to output information relevant to a verb in case that is what is coming next. So for example, it might output whether the subject is singular or plural so that we know what form of a verb should be conjugated into if that's what follows next, right? So what are the variants on long short-term memory? We have seen before is just long short-term memory, but not all LSTMs are the same as the above. In fact, it seems like every paper involving LSTMs uses a slightly different version. So the differences are minor, right? So one popular LSTM is adding peephole connection. So this means that we let the gate layers look at the cell state, right? So you can see over here, right? So here you can see the peepholes over here to all the peepholes over there to all the gates, right? And instead of separately deciding what to forget, what we should add new information to, we make those decisions together. So we only forget when we are going to input something in its place, right? So we only input new values to the state when we forget something older, right? So here a slightly more dramatic variation on the LSTM is gated recurrence unit. The next one is GRU. So this is Coethal. It is being introduced by Coethal. It combines the forget gate and input gate into a single update gate. Okay, and it also merges the cell state and the hidden state, right? Previously there was cell state, right? So now this is being merged and it makes some other changes. So the resulting model is simpler than standard LSTM models, right? So there are few of the most notable LSTM variants like depth gated RNNs, and also there are many other models actually. So like if anybody asks you that which is being the best, do the differences matter? It is basically the comparison of popular variants. So it is finding that they are almost about the same, right? So this is how it is being, it is being worked. So LSTMs are big step in what we can accomplish with RNNs. It is natural to wonder, is there another big step? So common opinion among researchers is there is a next step and it is attention, right? So the idea is to let every step of RNN pick information to look at from some larger collection of information. So if you are using RNN to create a caption describing an image, it might pick a part of the image to look for every word it outputs, right? So attention is not only the exciting thread in RNN research, right? So work using RNN's generative models also is very interesting, right? So I hope this is really helpful for you to understand about LSTM and its variants, right? So let us meet in the next session. So here in this video, we have discussed about LSTM and its variants. I hope it is very clear to you.
In this video, let us discuss about text wrangling. So just we are going to look like how to use Python for text wrangling. So all the machine learning models we used to pre-process the data, right? So similar to that, even in NLP, it is really required to do text pre-processing, right? So let us try to understand that in detail, right? So what are the pre-processing steps, or what kind of wrangling we can do with the text data, right? So let us start it. So first I have imported NLTK. From NLTK, I have downloaded Punch, WordNet, stopwords, average perceptron tagger, right? Okay. So I have taken an example of text. Machine learning algorithms can help in converting text to numeric feature vectors, right? So when I execute this code, I'm getting the same output because basically I'm trying to get the output of text. So when I write dot lower, so let me clear all this output now, right? So that would be really interesting, I guess. So let me clear the output. So this is basically the text. So what I'm doing now is text dot lower. So what I'm getting now, you can see that in the previous line, you can see capital M, right? Machine learning algorithm. So that is converted into lowercase. Now, when I write text dot upper, I can convert everything into uppercase letter. Text dot title, right? Text dot title. So what I'm getting, machine learning algorithms can help in converting text to numeric feature vectors. So what is the difference here? Capital M, capital L, capital A, capital C, capital H. That is what happening because we have given title, right? So this is basically about the case conversion, right? So the next one is about tokenization. What do we do in tokenization? Let us see. So this is basically the sample text I have taken. Text pre-processing is a crucial step in NLP. Cleaning our text data in order to convert it into a presentable form that is analyzable and predictable for our task is known as text pre-processing, right? So import NLTK dot send underscore tokenize sample text. So what is happening here? The first sentence is text pre-processing is a crucial step in NLP. And the second sentence is that cleaning our text data in order to convert it into a present form that is analyzable and predictable for our task is known as text pre-processing, right? So if I want to convert it into a word tokenization, now you can see that text is separate, pre-processing is another word, is another word, is another word, crucial is another word. So these are basically the tokens, right? Now I have used NLTK dot talk tokenizer, and just let me do that. Now again, what you can see is text pre-processing is a crucial step, right? So this is what we are getting. So now I have imported Spacey, and from Spacey, I'm loading encode web SM. So what is that? So after that, what I'm doing is text underscore Spacey is equal to NLP sample text, right? So what is the sample text over here? Sample text is this one, right? So after that, what I'm doing, obj dot text for obj in text underscore Spacey dot sense, right? So now in the next step, what I'm doing, text underscore Spacey, right? So I hope this is clear, right? So this is what happening over here. The same thing we have done with the help of Spacey, right? So in case if I want to remove HTML tags and noise, so I have imported request and request dot get, and just I have written one URL dot text, right? So the next step, what I have done is, in the next step, what I have done is I have imported RE from BS4 import beautiful soup, define strip underscore HTML underscore tags text. So soup is equal to, this is what I have written the code. Now let us execute and see what is happening over here, right? So you can see that this is basically the this is basically present in that particular URL, and this is what I'm getting. So this is the start of the Project Gutenberg ebook, the Bible King James Book 1, right? So this ebook was provided by David Whitger, right? So this is what I'm getting, book 01 Genesis, right? So now if I want to remove accented characters, I'm importing Unicode data. So define remove underscore accented underscore chars text. Text is equal to Unicode data dot normalize nfkd dot comma text dot encode ASCII that I'm asking to ignore, and decode UTF-8 ignore, right? So let me execute this code. And for example, I have taken I have assigned some accented text to A, and let me execute this. Now you can see that this is basically accented text, right? So now in case if I want to remove this accented characters, just I'm writing remove underscore accented underscore cars, right? So what is happening now? I'm getting the output as some accented text only, right? So import RE, define remove underscore special underscore characters, text comma remove underscore digit equal to false. So basically I'm making remove underscore digits equal to false, and then I'm writing pattern also. If not, remove digits else this one, right? And I'm asking it to subtract sub that pattern comma text, right? So when I do that, so I'm taking a sentence over here. Well, this was fun. See you at 7:30. What do you think, right? So now in case if I want to remove all these special characters, remove underscore special underscore characters from this, yes, basically remove underscore digits equal to true. So now you can see that I'm getting only the text, I'm getting only the string, I'm not getting any special characters over here. So when I write remove underscore special underscore characters, now I'm getting the digits also. In the previous case, I have written remove underscore digits is equal to true. So I asked it to remove the digits, right? So that's the reason the digits was being removed, right? So hope it is clear, right? So this is what being done by these things. And then let us try to understand porter stemmer. From nltk.stem, import porter stemmer. So ps is equal to porter stemmer and ps.stem. I have given some examples like leaving, leaves, left. So you can see that ps.stem leaving, then ps.stem leaves, ps.stem left. So what is happening now? I'm getting output as LEAV, LEAV, LEFT. So what does this stemmer do? This provides the, or this cuts this word, and it is just reducing, I mean, it is just eliminating this ing and just giving me the output. So here the problem is LEAV doesn't have any meaning, right? So in case if I write LYING, I'm getting LIE, right? This is fine. When I write for strange, I'm getting STRANG, which doesn't carry any meaning. Sometimes what may happen is when we do stemming, it may lead us to, it may give us some word that actually has some other meaning. So those are the complications with the stemming. Now import NLTK, PS equal to NLTK.porter.porter stemmer, NLTK.stem.Lancaster stemmer that I have written in LS, and define simple underscore stemming, text comma stemmer equal to PS, and then just I have written this function, right? So when I run this and I have taken, my system keeps crashing from yesterday, okay, yesterday, or crashes, okay. Presumably, we are not lying, right? Okay, so let me run this now. What I'm writing now, simple underscore stemming, yes, comma, stemmer equal to PS. My system keeps has changed into keep, crashing has changed to crash. From yesterday, presume we are not lying, right? We are not lying. So that has changed to we are not lying. So now simple underscore stemming, yes, comma, stemmer equal to LS. Now what is happening? My system keep crash from yesterday. So I think I'm getting the same other than this one, right? R is changed to AR. In case if I use limmatization, what will happen? So in lemmatization, it will take the root word which have the proper meaning. So from nltk.stem, import wordnet lemmatizer, WNL equal to wordnet lemmatizer, and help WNL dot lemmatize. So now you can see that what is happening here. Say for example, cars. Right now, car is changed to car. And when I try to lemmatize this boxes, I got the output as box. For running, I'm getting run. Ate, eat. This is brilliant, right? Because this is not possible with stemming. Ate is converted into eat. Then with the adjectives, saddest is changed to sad, fancier is changed to fancy. So the next one is about ineffective lemmatization. You can see that eight, fancier, fancier, and fancier, fancier, right? What is over here? Like what I'm trying to say is like here I'm specifying that which whether it is a noun or verb, just I have mentioned over here. Now I'm taking another, usually we use this example in all the documents. Yes is equal to, the brown foxes are quick and they are jumping over the sleeping lazy dogs. It looks funny. I'm going to tokenize it now. When I tokenize it, it is getting converted into tokens, which means the words. Now I'm going to lemmatize that. So what is happening now? The brown fox are quick and they are jumping over the sleeping lazy dog. Now I'm using the POS tag. What I'm getting the corresponding tag for each and everything. Say for example, sleeping means sleep plus ing. Basically it is verb plus gerund, right? So this is what I'm getting. Even for jumping, we are getting the same, right? So this is what we are getting. From nltk.corpus, import wordnet.add, right? So I am getting A, right? So define POS underscore tag underscore wordnet. And for this tagged tokens, I am doing, right? So when I do that, I'm getting for each and every case. What is this basically, right? We know what is what, right? So what is happening here? It is tagging with the POS, right? So you can see here, for verb, it is being written as B, and for adjective, it is being J, and adverb, noun. So everything is being denoted already here under this tag underscore map, right? So what are we getting now? I'm getting what I'm getting yan basically, right? So that is what I'm getting. Sleeping is basically verb. Lazy is basically adjective, right? So this is what actually happening, right? Sorry, adverb. Lazy is basically what is that? Lazy. Where is that? It is showing it as A, right? So we know that, right? Okay, fine. So the next one is about lemmatized text, and here we are for each and word tokens we are doing it. When we do that, we get the brown facts. You can see that here WNL dot lemmatize word comma tag for word comma tag in wordnet underscore token. So what is happening here? The brown fox are, right? So the R is converted into B. Quick and they are get converted into B. Jumping got converted into jump over the sleep lazy dog, right? So hope it is clear, right? So you can also try out something like this. Then WNL is equal to wordnet lemmatizer, and and here again I'm giving the lemmatizer now. So the same sentence, if I try to lemmatize underscore text of X, this is what I'm getting, right? The same thing, right? Fine. So this is what I am getting, right? Now the next one is that define remove underscore stop words. Text is underscore lower underscore case is equal to false. Stop words is equal to none, right? If there are no stop words in the sense here I have used English, right? If it is lowercase, what has to be done? Otherwise, what has to be done, right? So when I run this, then we write nltk.corpus words English, right? So this is being I, me, my, myself, we, our, ours, ourselves, you, you are, right? So it is showing some stop words, okay? And then in case if I ask it to remove the stop word, now what I can see, previously it was the brown foxes, right? So the is missing, the is removed, brown foxes, or, right, or is being removed because it is a stop word, quickly, quick, jumping. So over is basically a stop word that is being removed, sleeping, lazy dogs, right? So you can also try out that. So in case if you want to remove something specifically, you can do that, right? So stop underscore words dot remove the, stop underscore words dot append brown. And in case if you want to remove underscore stop words, yes, the lowercase equal to false and stop words equal to stop underscore words. So what is happening now? Since I have asked this to do it, I'm getting the foxes quick jumping the sleeping lazy dogs, right? So hope this is clear to you. So this is a simple notebook which is clearly explaining about text wrangling. Hello everyone. In this video, we are just trying to understand how to do machine translation. So what is meant by machine translation? So let me tell in simple words, we are just trying to convert from one language to the other language over here. So what is our objective over here? We are trying to convert from one language to other language. So the problem statement that I have taken over here is to convert a German sentence into its English counterpart using a neural machine translation, right? So basically, we are trying to convert German language into English. That is why it is called as machine translation. So the model, what I'm going to use over here is sequence to sequence model. So these sequence to sequence models are used on variety of NLP tasks like text summarization, speech recognition, DNA sequence modeling, and there are many more applications. So here, what are we trying to do? We are trying to translate some sentences from one language to another language. So what is input and output over here? Both are going to be the sentence. So the input sentence is going to be German language and the output sentence is going to be an English. So in other words, these sentences are a sequence of words going in and out of a model. So this is the basic idea of sequence to sequence modeling. So now let us try to understand. So this is basically the input sentence that is being in German, and I am using the model, and the output I am getting it in English. I do not know German, but still the meaning of it is it hard? So a typical sequence to sequence model has two components. One is an encoder and the other one is decoder. So both encoder and decoder are two different recurrent neural network models combined into one giant network. So you can see over here, this is basically the encoder and this is the decoder, right? So there are several use cases of sequence to sequence modeling. So let me give you some examples like speech recognition, named entity recognition, subject extraction to identify the main object from a body of text, then relation classification to tag relationships between various entities tagged in the above step, and chatbot skills to have conversational ability and engage with customers, text summarization to generate a concise summary of a large amount of text. And the last one is question answering systems. So what we are going to do is we are going to implement in Python using Keras, right? Fine. So let us try to import all the required libraries. So import string, import RE, from NumPy import array, argmax, random, take, import pandas as PD, and from keras.models, I'm importing sequential, from keras.layers, I'm importing dense, LSTM, embedding, repeat vector, and from keras.preprocessing.text, I'm importing tokenizer, from keras.callbacks, I'm importing model checkpoint, from keras.preprocessing.sequence, import pad underscore sequences, from keras.models, import load underscore model, from keras, import optimizers, import matplotlib, and then I'm just setting the option for display max column width as 200, right? So this is being done. What is the next step? We have to read the data into our IDE, right? So this is basically a text file of English to German sentence pairs, right? And first we will read the file using a function defined below. So I'm using this code for the function to read raw text file, right? So let's define another function to split text into English-German pairs separated by this. So we will then split these pairs into English sentences and German sentences respectively, right? So what I'm doing, I'm splitting a text into sentences. Now we can use these functions to read the text into an array in the desired format, right? So now the actual data contains over 1,50,000 sentence pairs. However, we will use only the first 50,000 sentence pairs only to reduce the training time of the model. So in case if you want to change the number, in case if you want to train on 1.5 lakh sentence pairs, you can do that, but I have taken only the first 50,000, right? What is the next step? The next step, so I have imported all the necessary packages, and the second step, I have loaded the data, right? So now I have to start with the text pre-processing. So basically it is nothing but the text cleaning step I'm going to start with. So there is an important step in any project. So that is especially in NLP. So the data, what we are going to work with is basically the unstructured data. So there are certain things we have to take care before jumping to the model. So the first step, what I'm going to do is text cleaning. So just look at our data, then we will decide which pre-processing steps have to be adopted, right? So DEU underscore English, and then this is the array output I'm getting over here. So we will get rid of all the punctuation marks, and then we can convert all the text to the lowercase, right? So that is what I have done, remove punctuation. So basically I'm trying to remove all the punctuation. So this is the output I'm getting now, and then I'm trying to convert it into lowercase, right? So once I do that, so here I have done two steps. One is about removing the punctuation and then converting to the lowercase. What is the next step? I'm going to do text to sequence conversion, right? So a sequence to model requires that we convert both the input and output sentences into integer sequences of fixed length. So, but before we do that, we have to visualize the length of the sentences, right? So we have to capture the length of all the sentences in the two separate lists for English as well as the German respectively, right? So this is what we are trying to do now. So quite intuitive. The maximum length of the German sentences we will try to figure out, right? So this is what we have to try to figure out. So what I identified is the maximum length of the German sentences is basically 11 and English phrases is 8, right? So let's vectorize our text data by using the Keras tokenizer, right? Fine. So now I have defined a function to build a tokenizer. So what will happen now? It will turn our sentences into sequences of integers. Then we can pad those sequences with the zeros, right? We can pad those sequences with the zeros to make all the sequences of the same length, right? So we will prepare the tokenizers for both German and English sentences, right? So this is what I have done. So a function to build a tokenizer, and then I'm preparing English tokenizer and this tokenizer, right? So once I do that, so just I'm trying to get the vocabulary size of English, that I'm getting it as 6,256, and this German I'm getting it as 10,329, right? So now this is the function to prepare the sequences. It will also perform sequence padding to a maximum length as I mentioned above, right? So now there will be a block that contains a function to prepare the sequences. So it will also perform sequence padding to a maximum sentence length, right? So this is what we are going to do: encode and pad sequences. So define encode sequences, tokenizer, length, as well as the lines. And then I'm writing integer encode sequences and then padding sequences with the 0 values, right? So now everything is being done. Now we can start with the model building. So while we build the model, we have to split the data into train and test set for model training and evaluation. So from sklearn.model_selection, import train_test_split. And then train_test is equal to train_test_split that I have imported. And this one I'm writing test size is 0.2, random_state, I'm giving it as 12. You can change all these numbers and see, right? So now it is time to encode these sentences. So we will encode German sentences as the input sentences and English sentences as the target. Why? Because we are trying to convert German into English, right? So it will be done on both the training set as well as the test data set. Now I'm preparing with the training data. So I'm encoding the sequences and this is what I'm passing it now. And then actually I'm preparing the training data as well as the validation data, right? Now this is the super cool part. We are going to define our sequence to sequence model architecture. So we are using an embedding layer and an LSTM layer as the encoder and another LSTM layer followed by a dense layer as the decoder. So you can see over here, I am building neural machine translation model now. So I'm building the model and here I'm passing these arguments in_vocabulary, out_vocabulary, in_time step, out_time steps and units. And model what I'm using sequential. Now I'm adding embedding, I'm adding LSTM, I'm adding repeat vector, I'm adding again LSTM, again I'm adding dense. So in the dense, I'm using activation function as softmax, I'm returning the model. So now we are using okay, so now what we are using is RMS prop optimizer because it is a good choice for recurrent neural networks. So I'm just building the model. I'm just building the model. Due vocabulary size, English_vocabulary size, due_length, and English_length, that is 512 I have taken. And then RMS prop learning rate, I'm specifying it as 0.001. And then I'm compiling the model. Optimizer, what I'm using is RMS. Loss, I'm using it as parse_categorical_cross entropy, right? So this is what I have. Done. So now you can have a look at the structure. Actually, I have shown over here. So there is for the encoder, we will be using embedding layer and an LSTM layer. And for the decoder, I'm using another LSTM layer followed by a dense layer. So here we have input, embeddings, encoder, decoder, dense, and then it is being output, right? So now what I have done is just I have used this. I have used sparse categorical cross entropy as the loss function because it allows us to use the target sequence instead of one hot encoded format. So one hot encoding the target sequences with the high vocabulary might consume our system's entire memory, right? So it seems we are all set to training our model. So we can try for 30 epochs, but I have taken only 10 epochs with a batch size of 512. You can also change with the several epochs and you can play with this hyperparameters. And also I'm using model checkpoint to save the best model with the lowest validation loss, right? So, and also I have done this early stopping. So file name, I'm saving it as model.h1. and checkpoint, model checkpoint, file name, comma, monitor is equal to val underscore last, and verbose I'm setting it to 1, and mode is equal to minimum, right? So then I'm writing history is equal to model dot fit train x train y, and then just I'm making the model to fit with that. So I have tried with the 10 epochs, you can try with 20 or 30, and you can see about the validation loss and all, right? So whatever is being better, that you can fix it up, right? So that is what we have to do, right? So once I do that, we can compare the training loss as well as the validation loss over here. So the validation loss, what is happening with this, that you can just look at this, what is happening to the loss over here, right? Finally, we can also load the saved model and make predictions on the unseen data, that is the test data. So what I'm doing now, right? So these predictions will be the sequence of the integers. So we need to convert these integers into their respective words. So that is why I'm defining a function over here, n comma tokenizer, and here what I'm doing, I'm converting the predictions into English actually, right? So I'm converting the predictions into English over here. And now let's put the original English sentences in the test data set and the predicted sentences in a data frame. Then we can randomly print some actual and the predicted instances to see whether our models perform. So randomly I have taken 15 sentence, and I'm really happy with that. Say for example, I feel cheated, I feel the, and like this is actual this is being the actual, and this is being predicted, right? This is being predicted. So we nearly starved. We were, so this is being still incomplete. Tom made Mary stop. Tom made Mary, right? Mary. I can't see Tom. I can't go that. I feel cheated. I feel the, we know our rights, right? Mary is my daughter. So actually I have tried only for 10 epochs. And if you try for 30 epochs, definitely that will really give you a very good result. You can try with that, right? So our sequence to sequence model does a decent job over here, but there are several instances where it misses out and understanding the keywords. Say I can see something like Tom, does Tom understand? So it is being stopped in Tom and all, right? So there are some misunderstanding also, misunderstanding the keywords also. So that are the challenges that we will be facing on a regular basis in NLP. And these are not immovable obstacles. So we can mitigate such challenges by using more training data and building it better. So what I request you to do is like change the epochs to 20, 30 or 40. And also while training the data, I have taken only the 50,000. You can try with 1 lakh or 1.5 lakh. And you can tell me like whether it is giving a good result or not. Hope you understand the concept. In this video, let us discuss about how to do POS tagging with the Keras. So we all know what is POS tagging, right? So part of speech tagging, right? So this is what we are trying to understand in today's session, right? So let me teach you like how to do that. Here I have used POS tagger using Keras and also a bidirectional LSTM layer, right? So I have imported NLTK, and then I have downloaded this tree bank, and then tagged underscore sentences is equal to nltk.corpus.treebank and dot tagged underscore sentence, right? So this is what I have done. And now we have to restructure the data a bit. So I'm going to separate the words from the tags, right? So I have imported numpy as NP, and let us also see how a sequence looks like, right? So before training a model, we need to split the data into training and testing data. So that is what we are going to do now. From sklearn.model underscore selection, import train underscore test underscore split, right? So once I do that, what I'm doing, Keras can also work with the numbers, not with the words or tags, right? So let's assign to each word a unique integer, right? And a tag, right? So for word and tag, a unique integer. So we are computing a set of unique words and tags and then transforming it in a list and transforming it in basically a list over here, and we are indexing them in a dictionary, right? These dictionaries are the word vocabulary and the tag vocabulary, right? So we will also add a special value for padding, right? I'm also adding this padding, the sequences, and also another one for unknown words, that is OOV. What is OOV? Out of vocabulary, right? So now let us convert the word data set into integer data set, right? So I'm converting the word data set into the integer data set, right? Okay. And then basically what I'm doing now is I'm converting the data set into integer data set. Not only that, and also both the words and the tags, right? And also both the words and the tags. So now you can see that Keras can only deal with fixed size sequences. So what we have to do, we have to pad pad to the right all the sequences with a special value 0, right? So we have to pad it with the special value 0 as the index and pad. So as the corresponding word to the length of the longest sequence in the data set, right? So let us compute the maximum length of all the sequences. And here I'm getting output as 271. So now we can use Keras pad underscore sequences. So from Keras dot preprocessing dot sequence import pad underscore sequences, right? So here what I have done is we need an embedding layer that computes a word vector model for our words. So word embedding means we have an idea about it. And then also we need a LSTM layer with a bidirectional modifier. So bidirectional modifier inputs to the LSTM the next values in the sequence, not just the previous, right? Not just the previous, right? And we need to set the return underscore sequences is equal to true over here. So you can see over here, right? So what I have done here is basically I'm writing return underscore sequences equal to true. So this parameter, so that the LSTM outputs a sequence, not only the final value, right? After the LSTM layer, we need a dense layer or fully connected layer that picks the appropriate POS tag. So since this dense layer needs to run on each element of the sequence, I have added this time distributed modifier. So from keras.models, I have imported sequential. From layers, I have imported dense, LSTM, input layer, bidirectional, time distributed, embedding, activation. And from optimizers, I have imported Adam, right? So this is the result I'm getting. I'm getting it as this one. So there is one more thing we have to do before training. We have to transform the sequences of tags to sequences of one-hot encoded tags, right? This is what the dense layer outputs. So this is what I'm writing the function as. This is the function that will do it, right? So now let us see like how this one-hot encoded tag look like, right? So the moment, this is what we were waiting for, the training the model. Now we are fitting with the training sequences, right? So let us now evaluate the model on the data that we have kept aside for testing, right? So that is what we are doing now. Now, in case here the accuracy what I'm getting is 99%. So there is a catch. A lot of success is because there is a lot of padding, and padding is really easy to get it right. So now let us take two sentences. I have taken running is very important for me. I was running every day for a month, right? So now let us transform them into padded sequence of word IDs, right? And once I do that, let us try to make the predictions now. So when I predict that, like it is actually pretty hard because we need to do the reverse operation for to underscore categorical, right? So this is how the prediction now looks like, right? So this is what I have defined logics to tokens, and like you can see that this is what actually it looked like. Now we are fairly acquainted with the Pentry Bank tag set by now, and we are probably disappointed with the result. So what is basically wrong over here? For most of the sentences, the largest pad is actually the padding tokens. These are really easy to guess. So hence the super high performance we are getting, right? So now let us write custom accuracy that ignores the paddings, right? So from Keras import backend SK. Now let us retrain adding the ignore underscore class underscore accuracy metric at the compile stage, right? So once I do it, now let us retrain it. Okay, so once we retrain it, now I have stopped the training, and here you can see that I'm trying to make the predictions over here. So here I have ignored the ignore underscore accuracy, right? So that is what I have done. Now let us see how the model actually performs, right? So now you can see that the results are actually better than the previous one, and they can also made it better, right? So here I have implemented POS using Keras as well as bidirectional LSTM. Hope it is clear to you.
This is the diagram for LSTM forward pass, hyperbolic tangent function. We are applying some weight, multiplying, and then processing through the layer. These are Hadamard product, and this is sigmoid function. This is 10x function. So these are activation functions. We are on each hidden layer. We are processing, applying some weight. Biases are calculated. Okay. That how far we are. That means loss prediction, loss function. Because we have to always compare with the distance of the actual and prediction. So it is always continuously in each hidden layer, in each activation function, it will calculate to predict the next word. As the name suggests, the forward pass and backward pass are unidirectional. Okay. Once data will be inputted, so you will get the output. Okay. It will not reverse back. Which process the unidirectional LSTM, which process the information in one direction, either on the forward side or on the backward side. Where the bidirectional LSTM process the data on both sides, persists the information. Okay, then it is feed forward. So feedback will be provided, and again the whole process will again reprocess, and it will be the text will be provided after some correction. Okay. Again, if you are not satisfied, then which part are uh, affecting the process to predict the next word or the text. So it will be removed because some weight and segment function will analyze activation function, and if it is less weight or some impact on the output, it will be removed or discarded, and it will be updated again. So all the LSTM tag work on a basic structure. Updating the basic structure causes the difference between various LSTM. Okay. This is point-wise multiplication dot product. The weights and the input will be multiplied to process in the next step. We have to add here point-wise addition. All the text will be added, concatenated to make some sense of the and one by one, all the sentences will be connected in the final before the uh, final output layer. Whole word will be connected, processed as a text. Back propagation through time in LSTM. These are input, these are weights, multiplication here, processing some activation function in the hidden layer, then again process. These three parts are called short term memory. Then it will connect it to with each other. It will create long short term memory. Okay. And either in the final different output layer, okay, we are providing different text for a. If it is a one line, it is a second line. This is the third line, third sentence. The whole sentence will be connected, provide as a whole text. LSTM, back propagation through time. We call it back propagation through time because we are repeating this process at each time. If observed carefully, this is similar to the normal back propagation process. You can use this pictorial representation of LSTM cell. This is previous layer, this is next layer, and this is current layer. These all layer are hidden layer, okay, but a single node, or you can say cell of the hidden layer, three hidden layer, are creating a short-term memory, which is connected through forward and backward pass. So data are again provided. The user will say that this is not correct. So again, all the data which is provided previously, it will be used reused. Okay. So the LSTM cell back propagation is different from the RNN because in each time stamp during back propagation, the values of the input gate, forget gate, and output gate should be updated. Okay. Values means weights will be updated. So which word is important, which is not important, we have to making some combination. These are the applications. Most of them language modeling, machine translation, handwriting recognition, image captioning, image generation using attention model. Okay, very important. In just like ChatGPT model, use this. Questioning, answering, video to text conversion, polymorphic music modeling, speech synthesis, protein secondary structure prediction for biological purpose. These are also protein homology detection, sign language, handwriting, grammar, speech, times, subcellular localization of. We have removed some drawbacks and advanced some LSTM architecture where by some remember gate. So LSTM deal with both long-term memory and short-term memory. By connecting both of them, it's created long short-term memory. And for making the calculation simple and effective, it uses concept of gates. Forget gate, it forgets information, which is not useful in a very long time. Okay, user are not using those words or not asking, so it will be removed. Learn gate, event, and you can say a current input and STM, short-term memory, are combined together so that necessary information that we have recently learned from the STM can be applied to the current input. Remember get LTM information, long-term memory information that we haven't forget, which is the main context of the user interaction. And STM and event are combined together to remember gate which work as updated LTM. Use gate. This gate also use LTM, STM, and event to predict the output of the current event, which work as an updated HTML. Context and event and all are same. Okay. That means in the long short-term memory, you can see we have forget, get, learn, get, remember, get, use, get. Okay. Event is wolf. So wolf and dog. This, if you combining this, so it will gives you 80% and 20%. So if you are training your model with some wolf data, so it will understand, update that this is not a dog, this is not cat. Okay, so dog cat mixing data or something. So it's depend on the what type of data you are providing. Okay, so it will give you some probability that dog like 20% and wolf for 80%. Okay, so finally you have to analyze with your common sense that this text is good or not, this image good, are correct or not. Okay, so according to that you have to update them. The actual mathematical architecture of LSTM is represented using this following figure. This is a same pattern which we will use. So mind functions, NH. This plus is connecting the two previous and current cell. Learn get HTML event combining information of event and HTML. Ignore the information which is not important. So learn get takes event ET and previous short-term memory as input and keeps only relevant information for prediction. Forget get takes previous long-term memory as input and decides on which information should be kept and which will be forgotten. Remember get combines previous short-term memory and current event to produce output. So this will combine HTML event together. So for next, say use get is used to combine the information of previous long-term memory and previous short-term memory to create HTML for next and still produce output for the current event. Encoder, decoder, attention. Okay. So what is encoder? The encoder is a kind of network that encodes. Okay. In this network, you can understand that uh, this is a neural network. So that is obtained or extract features from given input data. It reads the input sequence, okay, and summarizes the information in something called internal state vector. Okay, it will convert all the uh, sequence of text and one by one all the uh, words will be converted into a numerical table. Okay, and that numerical numbers 101 how much frequency if we are processing the whole text. So each word has some frequency and that frequency is calculated and noted under a table and the column will be the word name. Okay. So it will create a vector or you can say context vector. In this case of the LSTM network, these are called the hidden state and cell state vectors. We usually discard the output of the encoder. Okay, which words are not important. So in the encoder part, there are two types of neural network. which are working for um, back propagation and forward propagation. So encoder works for using forward propagation, and the decoder will work back propagation. So they have some three cell creating a short-term memory. Okay. So in this encoder, we will process only those words which are important for predicting the context, okay, or the answer of whatever the question asked. So encoder and only preserve the internal states. This context vectors aims to contain all the information for all input elements to help the decoder make accurate prediction. Okay, so the discard part, we have to remove those words under the encoder architecture, and then decoder are getting only those words which are important for predicting the answer. The hidden and cell state of the network is passed along to the decoder as input. Okay, cell state, this plus is the cell state. Okay, so they are connecting two words and uh, two cells for processing, and then one cell for feed forward. Okay, so it will just check in the cell that which word is important or not according to the some weights. So it will pass through the network along, and decoder will get input, and then decoder that something for decodes, interpret the context vector. It will convert the uh, actual word which will redirect to the table. Okay, where some detail wise uh, context or the text are uh, generated, and if the search keyword are matching with the table content, so it will be combined and just processed fastly, okay, as an as output to the user. So interpret decodes interpret the context vector obtained from the encoder. The context vector of the encoder's final cell is input. Encoder's final cell is input to the first cell of the decoder network. So in this context vector, whatever the important text or the word are there, so it will calculate the frequency and how much which word is coming frequently. So the related uh, context table will be hit, and then it will search for the whole theory, uh, whatever which is trained, uh, which is maintained in the database for training purpose. So it will use those text and process which will be are matching, and how much will be the probability for calculating the output. Okay, so using this initial state, decoder starts generating the output sequence. Okay, and these outputs are also taken into consideration for future prediction. Okay, so this output will be stored if the user will satisfied with the answer. So it will be as a reference. It will be stored. Okay, because if another time someone is asking same question, so it will just pick uh, fetch from the database and just uh, provide to the customer, sorry, for the user. So a stack of several LSTM units. Stack means just as you can understand that we are storing something uh, one above the one. Okay, so one, two, three, four, just like we are arranging the top level. So The stack of several LSTM unit, that means 3 units, input cell, output cell, and uh, current cell. So it will create a short-term memory, and all the LSTM will be in a stack. So it will one by one it will discard the those words which is not important, and it's just filtering for filtering purpose, because we have a large text, 2 3 lines of words, and we have to pick only 2 to 3 words. Okay, which is the which is very important for defining the context, in which context you are asking the questions. Okay, just like if we do not look in this decoder word, if we'll take from A to network, so to, along, the, and this is not related for any context. Okay, these are for grammatical rules. We have to focus only on decoder and encoder. So this type of word, okay, which is processed, and one by one it will be removed. Just like something, that, context, obtained, these are not important. These are verb, okay, and it may be noun, preposition, conjunction, the grammar's rules. Okay, so if we want to process fastly, so we have to just pick those, process those words, those parameters, which is important for processing the next text. Okay, for predicting, because we have to put only 2 3 or maybe up to 5 or 6 words. Okay, because uh, each word will be processed one by one, and it will take that in what context. Okay, even decoder can be work in the networking side also. So at what, if you are searching in chat gpt what is encoder decoder, so how a chat gpt can understand that you are asking with the context of AI, not a network related. Okay, in a mobile network there is also encoding decoding technique. In cyber security there is also encoding decoding techniques. Okay, so in multiple things, if in a language translation there is also encoder decoder. So at what context you are asking, you have to mention, otherwise it will confuse. You will not get a good output from the AI model, LSTM model. So if we are processing a large text, so all the text will be processed for a particular words will be processed to the decoders. Okay, then decoder will use those context vector, that how many times as, if in this whole text decoder and vector context are repeating much more time, if this text are related to the decoder, so decoder will be the will high will be the high frequency. Okay, you understand? So that means 4 5 or maybe 6 times, 8 times, which will be the mostly used in the text. That means the user are uh, asking for a particular word, so the only decoder will be processed through the encoder to as an input into the decoder model. Okay, then decoder will start reading from a trainable data. So in the trainable data, what is that what is where is the decoder uh, param is available, so related to the context against the decoder, what are the text are available, so they are start processing one by one and get the probability that which text is important for prediction. That means we have to provide to the user. Okay, so this is the process of from encoders to decoder, and then stack of several LSTM units is predict an output. Say y hat. Only y is the actual prediction, and y hat means we have uh, uh, predicted y. Okay, actual y and predicted y. Actual y means what data we have used for training, and when we testing our model, so y hat will be the predicted y. Okay, which is predicted y at a time step, or you can say time stamp. Okay, each recurrent unit accepts a hidden state from the previous unit and produces an output as well as its own hidden state to pass along the further network. Just like this, if these states, these cells are for encoder, and this is for a single circle of the neural network of the hidden layer. Okay, so first will be the input cell, then another hidden layer, and this will be the output. Okay, so these three cell are working as a short-term memory, and if it is a long uh, neural network, so three cell are creating a long short-term memory. Okay, and then only those words which is important, it will be processed as an input to the decoder model. Okay, so this is NLU, natural language understanding. This is NLG, natural language generating, like GPT model, generative pre-trained model. So how are you? You had putted three parameters, and if it is repeated, so one bag of words table will be created and the frequency will be calculated. So if uh, you are getting only no repeating frequency, so what are the type of closing statement? That means what? So what question marks? It means this context is related for asking something, questioning something. Okay. Then the meaning of you are, which is noun, which is so this type of thing will be calculated as per the grammar rule, and then it will be converted just like that. I am good. Okay, so all are connected and just concatenated again and again, because in text format we have to connect all the text word, then it will be the meaningful text. Okay, so one by one we have to concatenating all the text. Okay,